So let's start. Good morning. The first topic of today is clustering, that is putting documents in groups. This is important when we are trying to understand what a corpus is about or how things are related. And we will be discussing a few applications and two algorithms for clustering. So one example of clustering is clustering of search results. So what we are seeing here is a web page from a web search engine called yippee.com. All right, and in the next slide we can see it a little bit more in detail. And essentially what the search engine does is it is trying to put the results of the query, here the query is Clinton, into several categories. So there is Hillary Clinton, there is a Clinton church, there is Port Clinton, a city, there is an entry in Wikipedia about Clinton administration, but there are several pages also describing it. So the query obviously is very ambiguous, and the clusters of results are supposed to give the user an idea about where to go next. Similar things happen, for instance, in Amazon. If you put a query there which is very ambiguous, on the left you will see categories from which you choose. Is it electronics? Is it books? Is it something else? So the idea is very natural, appears in many places, and it's worth exploring a little bit in the context of how this kind of clustering could be done. All right, so here's another example of clustering where we do not cluster textual documents like search results. Instead, we cluster certain records. Okay, so we have a vector of numbers or a vector of attributes, and we would like to cluster this vector of attributes to solve the following problem. All right, so the problem is to develop marketing strategy in a new country. Okay, so answering the questions like what are the markets, how investments should be distributed, should the company go to many cities at once, or should it go to a few selected cities, and then which cities should it be, or which areas should it be? So in other words, focus of the marketing campaign is important, and how does the company determine such focus? So here's an example of clustering. So the example comes from McKinsey Quarterly. McKinsey is a large consulting company with worldwide presence. They publish their studies. Many of them are very interesting. So this is from about a year ago, and describes the application of a clustering technique to the marketing campaign. So essentially what they did is they established a number of attributes which we're going to list on the next slides, and then some distances between these attributes, of which of course physical distance was also important, and then created by a clustering algorithm a collection of regions. The next step was of course deciding where to start. All right, so they divided this into three classes. So mega regions such as Shanghai, large regions, and smaller regions. And depending on where the company wanted to go, they could start with either one, and they could choose, for instance, samples from clusters that share several properties. So if we go to the next slide, we see the description of the problem. So to gain economies of scale, many companies develop country-level strategies for each emerging market in which they compete. But in China, even nearby Tier 1, which means big cities, can differ radically. Guangzhou and Shenzhen, two urban cities of comparable size, are only 62 miles apart. However, in Guangzhou, a majority of consumers are locally born Cantonese, while in Shenzhen, more than 80% are Mandarin speaking. So you have difference in language, okay? And in addition, there are different tastes reflecting their different origins. So clustering on the basis of distance alone wouldn't be a good idea, but taking into account some other parameters such as language, cultural traits, media outlets, transport links contributes to creation of more robust clusters. So the idea is to create such clusters and then gain scale efficiencies by running operations within each cluster. So the idea behind this method is that dealing with clusters should provide better results. And indeed, the experimental point was that switching to a cluster focus can be dramatic, they say here in this report. In India, one leading consumer goods company recently cut costs by half by concentrating on 8 large urban clusters rather than attempting to plot strategy for 200 different cities, okay? So you see that, you know, that this idea of building clusters based on records, okay, on the vector of attributes, vectors of features, can be a very powerful idea that the company can save, you know, hundreds of millions of dollars or tens of millions of dollars in approaching the marketing and sales as you know, as a problem where we have some granularity versus, you know, trying to blanket a big country with a marketing campaign in a uniform way. All right, so the question is, how can one build such clusters? And what we're gonna see is that something similar to classification methods can be applicable here, all right? It's gonna work a little bit differently, but the idea that you have something similar to term document matrix, you have vectors, you have some similarity measures will be applicable. So another example is text clustering. So instead of reading a collection of documents, perhaps it would be better to group them first and then read only 1 or 2 of them from the group, and this would give you better idea what the documents are about. So such an example. We're going to see some additional examples here. So for example, all right, here we have a collection of medical abstracts, yes, which are, I mean, it's not a very big collection. It goes about, I think, 2,000 records. But obviously, it is not, it is not exactly clear what, what the topics of these medical abstracts are. So it would be nice to understand. It would be nice to understand how different records are related to each other. Do you have questions? Oh, okay. So what do we need to cluster? Well, we need a measure of similarity. We need some algorithm for grouping. And we need a criterion for putting documents into the same clusters. Okay, so in other words, what we have to do, we have to identify feature, create a vector of documents, define a measure of similarity of the vectors, and then decide when to stop. So let's look at how this can be done. All right, so there are some measures of similarity. If we have two documents, if they share a lot of words, that would suggest that the documents are similar. We could also notice that it's not just the word count, sort of the number of words that the documents share, but if the words that the documents share are more contentful, so in other words, they are rare words, it is more likely that that the documents are similar, so we can give a bonus for sharing some contentful word. And then another measure that we're going to discuss is cosine similarity, which is a very popular measure in information retrieval and definitely should be mentioned here. So we discussed before a term document matrix. Okay, so what we see here is that in this matrix, instead of having just marked the presence through 0 and 1s, we can actually put counts. So complexity appears twice in this document. Okay, in another document it appears 3 times. In the fourth document it appears 2 times, and the fifth 3 times. So we create this kind of matrix which tells us how the words in our dictionary, how many times they appear in different documents in the corpus. So this is the term document matrix, and there are different ways of representing it, of putting these numbers here. So before, for Bayesian classification, we mostly used the 0 and 1s in our examples. Here we have counts. We could also put something which is called term frequency times inverse document frequency that will be introduced shortly. So, so the question now is, if we have, say, a query that says complexity and algorithm, then which documents should be presented to the user? Well, this one has, document 1 has 3 counts, algorithm appears 3 times in document 1, it appears 4 times in document 4. So the question is document 4 a better choice? All right, so we need some kind of a criterion for deciding when a document is a better choice. Should it be dependent on the length of the document too, or just on the number of counts? So let's look at some of these similarity measures that can be employed to solve this question, that is, which documents should be ranked more closely given a particular query. So we obviously don't want all the words, okay, that's why we have the dictionary. So after ignoring, the stop words, we can then ask this question, which documents should be in the first place. So here the query is entropy, algorithm, and complexity. So entropy, algorithm, and complexity, and what we have here is document D1 and D4 as 2 possible candidates. So let's look at the methods that could be used to answer such question. All right, so one concept that could be useful is term frequency times inverse document frequency. So term frequency is how many times a given word appears in the document. All right, so term frequencies will be different in different documents. So to weigh it properly, okay, we also want to know how often given term appear in the corpus. So for that we introduce inverse document frequency. So document frequency is in how many documents a given term, given word appears. So this is DFW here. N is the total number of documents. That's why it's called the inverse, because we put the document frequency in the bottom of this fraction. And then it turns out that working with logarithm is better than working with raw numbers here. So we take the logarithm of it. So the formula for TF-IDF is term frequency of the word times inverse document frequency of the word. And this is a very common measure of importance of a word. So this would be this would be the number that we can put instead of the count in the term document matrix. So let's look at this a little bit more in detail, all right? So if we have inverse document frequency given by this formula, and if we have document frequency, which means in how many documents a given word W appears, if we have a word like A that appears in every document, then of course here we're gonna have N divided by N, which gives us 1. The logarithm of 1 is 0, and as a result, this multiplication would give us a 0. So therefore, as it essentially says, do not count very frequent words at all. And altogether, this formula gives us some graceful measure of the importance of the word. That is, the words that appear in all documents are not important at all, so because this will become 0, and therefore TF-IDF will be 0. Rare documents will have a relatively high score, because if the document appears only in one, if a word appears only in one document, then this measure is n divided by 1, so it's a logarithm of n. So with a large number of documents, this will be a relatively high score. All right, so this would be one of the tools that we can use to put numbers in term document matrix. So the next question is, how do we measure the similarity? So the first measure that we mentioned would be counting the shared words. So if we have a term document matrix like this with labels, we have a new vector, we can measure the similarity by counting the overlap. So here we have 1, 0, 1, 1. Here we have 1, 0, 1, 0. So there is an overlap of 2. So we put the similarity score here. So essentially, essentially what we are saying here is that similarity is the product of the vectors. It shouldn't be vector product. It should be products of two vectors. So it's a dot product or inner product. And we can define it mathematically as the sum of the new vector elements. So these are the vector elements. And here we have the appropriate row of the term document matrix. So we are comparing the row document I. So the document I is here, and multiplying it by zeros and ones, sort of the binary representation of elements in the document I. So that's why we get the sum from j equals 1 to n, the end of the size of the term document matrix, not counting the classes here. of Vj times Bij. So I is the ith document. All right? So that's the definition of similarity by shared words. Now, we learned a moment ago about TF-IDF, so what we can do now is we can add some bonus, okay? So the bonus can be given by different formulas, and in this example here, what we have is the same formula as before. So essentially here we care about the overlap, but now for rare words, okay, we add inverse 1 plus inverse document frequency. All right, so it's actually not inverse document frequency. It's something like inverse document frequency. We don't have the logarithm here. But in principle, we could have added also the inverse document frequency. So the idea is that if the if the term is very common, all right, then we basically, this would be this would be infinity. So 1 over infinity is 0, and this sort of is reduced to the previous measure. If the term appears only once, then we're going to have 1 plus 1 over 1. So we are doubling the score of this part in this particular place. So yeah, so that's the idea that, of having a bonus. So we are giving a bonus to rare words, to words that appear once or twice or 3 times. And the more times the word appear in the corpus, the less bonus we give to this word when measuring similarity. So that could be yet another similarity measure. So now we can introduce also a cosine similarity. And what we are doing here is, again, the idea is the same. We look at the overlaps, okay, which words overlap. But what we do is we're going to normalize it by the length of the vector. So we want something that would be between 0 and 1. And to do so, we have to put some normalizing factors. And these norms that we're going to put at the bottom of these fractions will do the work. So let's look at the details of this. All right. So here we have the full definition. All right. So we introduce this term frequency times inverse document frequency factor in this spot here, and then we normalize using the sum of wj's for each particular vector. So we can check that this indeed is this expression indeed would be behaves like a cosine function. All right. So this is the cosine similarity, and there is more than one way of introducing it. This is the one that involves a term frequency and inverse document frequency. If you have a binary vector, you would simply have this expression, and your norm would be would be also the length of the vector, but it would be just measured as the square root of the binary sum of the non-zero coefficients. So it would be, the formula would be similar, and the behavior of it would be similar, but of course, depending on how we measure similarity, we might get different results when we want to cluster documents according to similarity. So what works is an experimental question, and well, people try different similarity measures. Okay, so similarity of binary vectors is between 0 and 1. The cosine similarity, if you define it using arbitrary vector, could be between -1 and 1. So not only the value can tell you how similar they are, but also how dissimilar they are. So if -1 would mean that they are very, very different. So let's switch to, so now that we have some of the similarity measures, we can next talk about clustering. So in classification, we had classes like finance, sport, politics, earnings, and we designed some algorithms like naive Bayes to put new documents in appropriate class based on the data that we use to learn the parameters of the algorithm. All right, so here we do not have labels, but the idea of using some measurements to group things together is very similar. So what we have instead is we have sort of a document collection, and what we want to do is create clusters of these documents, not necessarily labeling them, although that would be nice, but just to sort of have some sense of similarity between the documents in the cluster. So we don't have to examine every document in the collection. Instead, we can just examine 1 or 2 documents per cluster. So how do we cluster? Why do we cluster? Well, we cluster because we want to put some order into search results. So we saw that. We do it because we want to pre-process. So we get a lot of documents from some source, and we would like to extract the gist of these documents. So the first step could be clustering of these documents and then possibly summarization. We will not talk in these lectures about summarization, but it is a very important idea. So for instance, let's assume that you follow certain news. This could be political news, this could be financial news. The same piece of information might be repeated many, many times. You don't have time to read it. So instead of reading everything that comes looking for a new important piece of information, what you do is you cluster the pieces of news around different topics, and then you summarize what have been learned so far. And if a new important piece of information comes, then it should differ sufficiently from the summarized document that it can be brought to your attention. And then again, with this new piece of information, it can be added to the summary, and you can wait for the next and important piece of news. So this would be one example of using clustering as a pre-processing task for summarization. Suggesting other relevant news articles. So Google, Bing, Yahoo, they all do it. They create clusters of similar documents. If you click on one of them, they're going to suggest possibly other documents from this cluster or from a different cluster if it turns out that people who like reading about movies, let's say they also like reading about golf, then they're gonna suggest you, an article about golf, about recent changes in golf rules. finding what customers are complaining about. This is also very common. You work for a company, the company started to implement some electronic records for customer problems. Suddenly you would like to analyze these records. This is your task. This is very common right now in the United States. So you get 1 million records and you want to understand what it is that is important, what it is that is most frequent, which of these were solved, which of them were unsolved. Since you have no idea what is in these records, you cluster them, and then you look at elements of the cluster and design algorithm for analyzing a particular set of documents in the most important cluster or clusters. And we saw an example from McKinsey about marketing, but clustering is big in statistical analysis, economics, and biology. I know too little about biology, but for example, in economics, we cluster locations according to certain criteria. So we saw it in the marketing campaign, but we cluster, for instance, little cities around big cities and create major statistical areas for on which statistics is done, and which are used in economic planning. All right, so the first algorithm for clustering would be hierarchical clustering, all right? So we have a collection of documents, since we know how similar or how dissimilar they are, there is some geometry in this collection. It would be a multidimensional geometry because our vectors are multidimensional, but of course we can't represent it here on the flat screen, so we just use distances. And basically what we do is we put things which are closer, which are more similar together. So in our first step, we put B and C together, as you can see here, because they are very close. These two guys, D and E, are also very close, so we create a cluster. All right? So once we have these clusters, so we have this cluster and this cluster, we can then ask, well, what is close next? Well, F seems to be close to D and E in this picture, so we add F to this guy. And then once we have this cluster and this cluster, well, these two guys are closer than the A, so we can put them together, and finally, the cluster that has all documents would be A, B, C, D, E, F. All right, so the idea is very simple. You do it, the natural stopping point would be when you have all documents, but of course, you would like to stop somewhere in between, because if you have all documents, that you haven't accomplished much. You had all documents at the beginning anyway. So the natural stopping criterion would be either to have B, C, D, E, F, and A, or to have possibly A, then B, C, then D, E, F. So depending on how much bandwidth you have to analyze the clusters, you would introduce different stopping criterion. So the number of clusters would be a very natural stopping criteria. And a rule of thumb is that you want the number of clusters to be about square root of the number of documents, all right? So here we have 6 documents, which would mean that you want either 2 or 3 clusters. All right. So this was the top-down clustering method. All right, so before we go to k-means clustering, let me make some comment about it. Notice that to do this clustering, you really have to compare, you have to have the distance between every vector every vector representing a document. So if you have 1,000,000 documents, that means you have to compute the distances between every pair of them, and that might take some time. If you have even more documents, you know, this time would be even longer. So there is an alternative. Instead of doing stuff top-down, you can do stuff bottom-up, and this is where the k-means clustering comes to play. So essentially, you start by distributing all documents into different bins. So choose your k, all right? For example, the square root of the number of documents, or if you have some other information about the number of categories that you care about, you can use this as the k. And then you go through several steps, and it's an iterative algorithm. It doesn't always give you the same results, but it's relatively cheap. So the algorithm consists of the following step. First, you distribute randomly the documents among the bins, then compute the mean vector for each bin, all right? So essentially you say, okay, what is the average of all the documents that I have, all right? That would be like a point in high-dimensional geometric space. You compute now the similarity of each document to each of these mean vectors, all right? So it might turn out that the document in a different bin is actually similar to the mean vector of another bin. If that's the case, then you perform this move, okay? So essentially you move each document to the most similar bin, where similarity is given by similarity to the mean vector. And you repeat the process. Eventually, this process should stop, and you will have clustered your documents among k bins. So an example of a mean vector, so if we have the documents from 1 to n, for example, like 1 to 3, 3 to 0, 1, 1, 1, then the mean vector, if I did my computation right, should be, okay, so here you have 1, 3, and 5. So 5 divided by 3 should give us 166. So this is correct. 2 to 1 divided by 3 gives us the same. And 301, which is 4, divided by 3 is this number. Yes. So essentially we do coordinate-wise addition and divide by the number of vectors. So that's how we obtain the mean vectors for each bin. And if we have two vectors, well, we can compute similarity. Again, I mean, for instance, performing, coordinate-wise, or performing the mean, or computing the mean differences. So there is, okay, so once we have this method, yes, what happens is that in the step where you move each document to the most similar bin, you essentially rearrange the documents into these clusters. You do something with this cluster, and then you do rearrangement rearrangement again. So let's look at an example. So here we have 5 documents, okay, and we represent the documents just by a number instead of a vector to simplify our computation. We're going to be doing 2 means clustering, and we start with randomly assigning documents to cluster 1 and cluster 0 and cluster 1. So 0, 4 is in the first cluster, 2, 3, 4 is in the second cluster. We compute the mean, so the mean of this is 2, the mean of this set is 3. Now we compare and reassign to the closest mean. So what is closest to this mean? Well, 0 is closer to 2 than to 3, and 2 is closer to 2 than it is to 3, but the other documents, 4, 3, and 4, all right, will belong to the bin, will belong to the cluster number 1. We repeat the process. So the mean of 0, 2 is 1. The mean of 4, 3, 4 is 3, 6, 7. And we do reassignment again. So what is closer to 1? Well, 0 is closer to 1 than to 3.6. And similarly, 2 is closer to 1 than 3.6. 3 is closer to 3.6 than to 1, and similarly for 4. So therefore, we get the cluster 0, 2, 4, 3, 4. This is the same cluster, so we are done. So this is the k-means algorithm. It's relatively simple. It is not very computationally intensive. You might get different clusters, though, depending on how you start. So as a bonus, of course, we can get a classifier out of it. So because now that we have these clusters, we can compute the composite vector for each cluster, and then when we have a new document, we essentially put it to the cluster which is closest to the mean of previous, to the cluster which has the mean, the smallest difference between its mean and the new document. All right, and as I said, the computation is relatively fast. So one example of it would be to do 2 means clustering of the earning reports. And if we do that, we're going to get 2 clusters, and the representative words from each cluster. In one cluster, we're going to have exchange, PCT, share, sale, dealer. In the other, we get, some not so interesting words like and, up, and, but also meet and sale. So some of the words can be repeated, as we can say. So again, if we do it for 12 clusters, we're gonna get cluster sizes of this. We won't get equal number of elements in clusters, as we can see here, and then the more descriptive words are written on the right. So cluster number 1 has 110 documents. It is represented by country, sale, interest, net, and share. These are not necessarily very informative, so to put a real label on it, you would really have to examine each cluster. Here is an example with 134 clusters, and we can see that the clusters from 1 to 4 are all about production, but maybe production of different things. This would be, say, the grain production, that would be steel production, this could be gold production. And the clusters are much smaller. And finally, if we continue this clustering process and we run it with 634 clusters, you know, most of the clusters will just have one element, but some of them will, like here, exchange will have 11 elements. So again, the question is where we stop, and there are several criteria for it. The easiest one to remember is square root of the number of documents. Here's another example of k-means clustering coming from Wikipedia. And in this case, k is 3. And what happens is that you start with some initial means, okay, which are randomly generated within the data domain. So in this case, instead of assigning documents to bins and then computing the means, this version of the algorithm starts with, you know, putting some random means in the space and then clustering around these means. So these are the 3 points in space, and we associate every document to the nearest mean. And so this guy is closer to this guy than it is to this one, so therefore it gets assigned into this red cluster. And similarly here, this one is closer to this guy than it is to this one, therefore it gets the green color. All right, so that's what's happening in the second step. So the beginning is different. Instead of starting with random assignments of documents into the clusters, we start with a random choice of the means. And then the process continues the way it was described before. That is, we find the mean vector or the centroid of each of the clusters and then reassign the document to the new centroid. So the centroid of this guy is here, the centroid of this guy is here, and similarly for the blue. And again, the documents are partitioned by the distance to the centroid. So what you can see here is that, you know, this space, you know, got rearranged, but and some of the documents moved. Okay, so these documents didn't move, but the space got rearranged here. However, since the mean moved from here to here, suddenly these two green guys get closer to, one of them gets closer to the red guy. So the bottom line is that what we have here is sort of the iterative algorithm that converges relatively fast. It's relatively easy to remember. You start either with, you know, with random assignments into cluster or random choice of means, and then you repeat the process of moving documents to the closest mean, computing the new mean, and so on and so forth until it converges. All right, so this is the algorithm. What is interesting about this algorithm is that it's also useful for, this idea of, you know, starting with some random choice, either random assignments to clusters or random choice of means, and then iterating until something converges is very common. And we're going to see it in the next lecture in the expectation maximization. In most cases, there is no guarantee that the final result will be optimal, but if the computation is cheap, you can try with different initial parameters, and then, of course, you increase the probability that you're going to hit on the optimal division of documents into clusters. All right, so these are notes and a summary. So k-means clustering has been used successfully in market segmentation, computer vision, geostatistics, astronomy, agriculture, and many other places. So it's a very useful algorithm to know. It is often used as a pre-processing step. And as what we mentioned before, the number of clusters equal to the square root of the number of data points is a good rough rule of thumb to remember for when doing clustering. So let's look at expectation minimization clustering. All right, so this is going to be a little bit more complicated, all right? But the idea is the following. In the previous examples of k-means clustering or the top-down clustering, we put every document in one cluster. Here we're not going to do that. Instead of putting a document into a particular cluster, we're going to assign a probability to a document being in a cluster. So we can say we are not sure that this document will be in cluster 1, but we can say we are 90% sure that it should be in cluster 1, but 10%, there is a 10% possibility that it's in cluster 2. So this essentially what happens in expectation maximization clustering. So this is a soft clustering method, not a hard clustering method like before. And here we have an example. So we have document vectors. So again, I mean, to simplify things, we just have numbers here. So we have the first vector is 0, the second is 1, third is 2, 4, and another vector is 4. We start with some random means, and now we ask the question, what are the chances that this vector 0 is generated by a cluster with mean 2 versus mean 3? Well, this is a small number, yes? So it is much more likely that this vector was generated by the cluster with mean 2 than the cluster with mean 3. All right? So since we know that the vector was generated, then the probabilities of generating by first cluster or the second cluster, the sum of probabilities has to be 1, and the assignment, the computation of probabilities is provided to us by a formula that we're going to see in a minute. But the bottom line is that we can have 90% certainty that this was generated by first cluster and 10% then that it was generated by second cluster. On the other hand, if we look at these last two vectors who have mean of 4, well, 4 is much closer to 3 than it is to 2, so it turns out that this gives us about 80% probability of being generated by this particular cluster. All right? So, the E step in this soft clustering method is the computation of probabilities that a given vector is generated by a cluster with a particular mean. And then what happens next is, again, we estimate the new means. So how do we do that? Well, we essentially take the values here and use these guys, this vector, as collection of weights, divide by the number, and this gives us a new mean. So we're going to see it in a formula in a second, but the bottom line is that the process is the same as we had before, except that now we have to into account, we have to divide the credit between different clusters. So we compute the new means. Now we have 1.3 for this cluster and 3.3 for that cluster. So essentially things grew further apart from 3 to 3.3, from 2 to 1.3. And this, of course, means that the probability of vector 0 being generated by 3.6 decreased, but the probability of being generated by vector by the parameter 1.3 should have increased, because here we had this change from 2 to 1.3. So we repeat this process, alternating between E steps and M steps until the process stabilizes, and so we have computed the parameters and we have computed the soft assignments to clusters. So we can essentially say with certainty that that this vector is in the first cluster, but for some other vectors like the vector number 3 with value 2, we can assign it with 70% probability to first cluster and 30% probability to the second cluster. So this is a soft clustering method. So let's look at some of the details here. All right. So again, this is just the description of, okay, so this is Q11, this is the explanation of the dot here. So this would be Q41, corresponds to vector number 4, and these are the probabilities of the vectors, this guy and this guy being in this cluster. So this vector has a probability 90%, this vector has a probability of 20%. All right, what else? This is the comment that I made before. We do not know which documents belong to which cluster. We only know the probabilities. So a document can belong to cluster 1 with the probability 90% and to cluster 2 with the probability of 10%. So in each step, we compute the likelihood of data being generated by cluster 1 and cluster 2. So essentially, we estimate, what are the chances that this vector was generated by a function with this parameter. All right, and how we get these parameters, these are the formulas. All right, so we assume that these clusters have something to do with the Gaussian distribution, and the formulas for estimation are derived mathematically. Some of it we're going to derive later today for the binomial distribution, which is similar, but some of it would require probably another hour of mathematics, and we don't have it, so I will not present it. But in any case, the point here is that these formulas are given. They would be different for different distributions. So depending on what distribution you assume you are dealing with, you would get somewhat different formulas here. So this is soft clustering. Well, the assumption in the example that we use is that this sigma in the normal distribution is equal to 1. So this is just to clarify things. So couple of points about expectation maximization. It is not one algorithm. It's a collection of algorithms for machine learning. Different distributions will have different formulas for M step and for E step. There is a common idea of switching between E step and the M step. So the expectation step, although I prefer to call it the estimation step, and maximization step, that is the explaining the data using the parameters. There is no guarantee that EM generates the optimal results, but it works very well in practice because, again, the algorithm is relatively cheap in the computation requirements, so you can experiment with several initial starting conditions and actually get the optimal solution that way. We're gonna see this in the next lecture. So the final topic of this first lecture is I want to show you a new technique for soft clusters exploration called topic modeling. So the idea here is the following, that we view documents as generated by particular topics. So we think of it that there is a topic that we can call earnings, or we have a topic that is called sports, all right? And these topics have words associated with it, all right? So say football can be a word associated with the topic of sports with very high probability. So in other words, if you have an article about sports, it's very likely that that the article would mention football. I mean, very likely here could be, say, 10%. There are many, many articles, yes? And it's also relative, because you can also imagine that an article about earnings can also mention football when they discuss the earnings of football clubs, and some of them are actually publicly traded. So there is a slight possibility that the discussion of earnings will also mention football, but the probability is much lower. Let's say it's less than 0.1%. So the idea is that we have the topics, we have the words which are associated with the topics, and then the documents are essentially collections of words derived from different topics. So documents are documents are topic mixtures. All right, so that's how we model our collection. So here we have an example of a document, all right, and at the bottom we have topics, okay? So the topics are collections of words that are associated with with a particular topic. So arts would be a collection of words, budgets would be a collection of words, children has some collection of words, and education has a collection of words. You're gonna see it in a second. So now what we see is that the document, all right, is associated with, it's essentially a mixture of topics. It's a mixture of colors, yes? So for instance, 1.2 million here obviously is associated with a budget, all right? William here is mistakenly associated with education. It probably comes from the fact that there is Williams College, all right? And so that would be the association with education. So this, partition is not perfect, but definitely the word foundation is associated with budget. So is service, all right? Philharmonic would be associated, or New York Philharmonic would be associated with arts. So, all right, so that's the view of the document, okay? So the view of the document is that it's a mixture of topics, and some probabilistic algorithms are used to analyze a collection of documents as a collection of topics, and each document, as a mixture of the words from each topic. Okay, so here we have the words. So arts are associated with words like film, show, music, musical, actor, York, theater, actress, love. Okay, so this set is derived automatically. The label, well, we put the label on it because we need labels for things, but typically these labels are not present. You do not get a label from the machine. Then another topic here, we have million tax program budget, spending, money. All right, we can call it budget. We could have called it money or money related, yes. Children, so we have the word children, women, people, child, years, families, parents, welfare, men, percent, care, and life. All right, I mean, this could have been called people. It would be fine too. The point is, it's just a collection of words with some probabilities attached to them, which we are not showing. And then the topic, which is called here education. So we have school, students, schools, education, teacher, high, as in high school, Bennett, which was the secretary, who was the secretary of education, Namphy, I don't know what that is, president, elementary, and Haiti for some reason. So, so that's, okay, so this is the idea that you essentially analyze a collection of documents as such a mixture. There is a very nice collection of tools for deriving topics, and we're gonna look at, I mean, there is more than one set of such tools. So we're gonna look at them right now. So what you see here is the same, what you see here is the same table of abstracts, of medical abstracts, yes, that I showed you before. And what we're gonna be doing is trying to make sense out of these abstracts by applying topic modeling to them. And I will be using the Stanford Topic Modeling Toolkit, which I find the easiest to use. The explanation of how to use it is on the web page. If you have to do some kind of analysis like that, that would be a great starting point. So essentially what you see here, it's a very complicated collection of text. And we will try to make sense out of it by applying the topic modeling toolkit. All right, so here we see an example of the program. So essentially the program, you specify the parameters of the program, such as which words you want to keep, how many stop words you want, and then you can run this program and obtain some idea about what the collection is about. So this gives you an idea of how the program looks like. It's a very simple program, and the only thing you have to specify is the name of the file and the parameters of the file. All right, so I'm starting the topic modeling toolkit here. So it runs in Java. It comes in a jar. That's the start command. All right, so once this jar is running, you get the screen here. So the first script shows us the number of records. So we have 1,550 documents here in the collection. The second screen tells us what are the significant words. And we can explore the collection, the topics that were created by looking at this, at the topics. All right, so here we have topic 0. Okay, has model, method, interact, approach. So this is about modeling something. So the first topic deals with methodological issues. Here the second topic is about rDNA and some genetics. Topic 4 talks about, well, it goes a little bit too fast, so we're gonna run it again. But in any case, we have a bunch of topics here that are associated with certain weights, all right, which could be translated into probabilities. All right, so if we look at, see, where are we here? right, so let's run it again. And let's look a little more carefully at these topics. So we are exploring the topic distribution. We're going to have about 30 topics. Okay, so here we have topic 0, which is essentially model, method, proposed study. So this refers to essentially what was done. It doesn't tell us, and Bayesian method possibly used. So this is a description of that we are dealing with the studies. All right. The next topic. Okay, so if we look at can't seem to stop the movie. Let's see. All right. So for instance, here we have the topic 4, which is method, technique, circular primer detection. So this is again about methodology. The topic 3 is about concentration, samples, organic measurement. So again, a collection of different words. Topic 6 is about stuff like activation process and mentions calcium receptor, kinase, stress, and pathway. So topic 9, cDNA, transcripts, cloned codon. So this definitely refers to genetics. So altogether, what we see here is that by running this kind of automated analysis, we get some idea about what the documents are about, how they are structured, and we can then decide that yes, we're going to be interested mostly in genetics, so we're going to try to get first the documents related to genetics. All right, so that is the new technique called topic modeling, and the tool that I used is the Stanford Modeling Toolkit. So again, I mean, the idea is that documents are viewed as mixtures of different topics, and words belong to different topics with some probability distributions. All right, so to summarize the clustering, what are the important ideas here? Well, that we can do it top-down or bottom-up. All right, we can have hard clusters, as we have seen in the original k-means algorithm, or we can have soft clusters, as we have seen in the short discussion of expectation maximization. We discussed k-means clustering, so this is something that almost always appears on exams. And we started a discussion of expectation maximization as an example of soft clustering, another example being topic modeling. So that will be it for this lecture, and let's take about 5-minute break, 5-10 minutes. All right, so we will explain expectation maximization at least some intuitions behind it, using the example of biased coins. There will be quite a bit of elementary probability calculus in this lecture, but I hope that this is going to give you a better intuition about, how mathematics can be useful in dealing with text and learning the parameters that we need to apply machine learning to text processing. We will not talk about documents per se in this lecture. However, the whole thing is applicable, for instance, in the context when you have to learn the parameters of logistic regression. If you remember from a previous class, we discussed how Watson evaluates candidates, okay? So there is 550 features, then logistic regression is applied to the value of these features, and the final score is computed, and if the score is bigger than 70%, Watson believes that that is the correct answer to a Jeopardy question. Now, the parameters, the weights for features on logistic regression in the logistic regression model used in Watson are learned using the expectation maximization algorithm. So it makes sense to go a little bit deeper into seeing what is involved and to see a little bit of the mathematics behind it. Plus, it's a good refresher on elementary probability calculus. All right, so we will be dealing with coins, all right? And just to get some intuition, let's think about the following two problems. So we toss a coin 100 times, all right, and we get 76 heads and 24 tails, all right? How likely is it to happen if we have just a regular unbiased coin? Or can we assume that there was something done to the coin, when we get this 76-24 distribution? How do we solve this kind of question? All right? So this is one example. We just have a series of tosses, and we want to understand how likely it is that this series was generated by an unbiased coin. All right? In the second example, we have two coins, okay? So one gives us 60% heads and the other 45% heads. The first one is tossed 4 times in the series of 10 tosses, so we have 40 tosses, the other 6 times in the series of 10 tosses. Can we conclude that any of these is biased? All right, so this is still the question of the same kind that we had here, except that the numbers are now, instead of 76%, are smaller, 60% and 45%. But the other question is going to be more important. What would happen if the series was 10 times longer if we had more data? All right. So these are the questions that we need to have some intuitions about if we want to understand the ideas behind expectation maximization. So the ideas there are that usually you can conclude quite a bit from even a small number of data parameters, but the more data you have, the more firm your conclusions will be. So let's look at these questions, and then at some point we're gonna switch to the problem of clustering, where the clusters will be coin tosses, and we will be estimating the parameters, the biases. All right. So if we have a collection of tosses, yes, sort of a very long series, I mean, if we look at it like that, there is no way we can guess whether the coin was biased or not. I mean, at least I can't. Maybe you could, but I doubt it, yes. All right? So, altogether, I mean, we are not well equipped to answer such questions just looking at the sequences of 0 and 1s. Because it could be, you know, for one thing, if we see that, yes, it could be a biased coin or unbiased coin, but it also could be two coins, all right? Maybe these are two coins with different bias and the average is just, you know, 50-50. So what is it that we can conclude from such series? And we would like to derive such conclusions automatically. So how do we test it? All right, well, we can look at averages per row. All right, so we take, you know, some parts of that series and we generate the average per each row. And, well, maybe we could conclude something from that. All right, but still, we would need some mathematical apparatus to tell us whether our conclusions are firm. On the other hand, people are very good at visually estimating things. So if we take the series that you saw in the previous chart and we put it in a diagram like this, yes, so these are the averages of each row, it seems pretty obvious to us that this is a biased coin, yes, because it looks like, you know, it's somewhere, you know, the bias is somewhere here, yes, could be even here. I mean, we don't know exactly where the bias is, but it's unlikely, very unlikely that it's a regular coin given that we only have sort of a few spots below 0.5 and many, many points above 0.5. So the conclusion is relatively obvious here, but we don't know yet how firm our conclusion might be. If we have more data, well, we can probably guess the parameter, yes? We can, you know, from looking at this diagram, we can guess that the parameter is that, you know, that this coin should give probably around 60% of ones and 40% of zeros, all right, based on a diagram, on the diagram that we are seeing here. So the more data we have, the easier it is to be certain of your conclusion. So now let's do some math and let's sort of estimate exactly the chances of, you know, of getting, you know, 76 heads in 100 coin tosses or, you know, or some other, or the probabilities of getting some other series of heads and tails or zeros and ones. So the chances of getting 10 heads in 10 tosses with an unbiased coin would be 1/2 to the 10. This would be probably a little bit bigger. And there is a general formula for k heads in n tosses, yes? So you probably have seen this. Correct? I mean, have you seen this binomial formula and the probability estimate by the binomial here, where p is the probability of a success and 1 minus p is the probability of a failure, and we estimate the probability of k successes in n trials. All right? So we have this, you know, so we have this formula. This gives us some idea about the probabilities, and we're going to be working you know, from this formula and from the reverse of this formula. In practical applications, when we have a lot of cost coin tosses, we do not really want to compute 100 factorial or even 60 factorial. So instead, we can use pre-computed functions, for instance, in Excel or in any other you know, math program that you wish to use. So now let's go back to the question of you know, getting 76 successes in 100 trials. How do we go about it? Well, in Excel we have a function called binomdist, so binomial distribution, and we can simply plug in various numbers and get answers. So here is an example of probability of the number of successes in 4 trials, okay? So the probability that the number of successes in 4 trials is not more than 0, okay? So is 0.625, so basically it means that this is the probability of no success, probability of 1 success, probability of 2 or less successes, and here the probability of 4 or less successes is 1. So this, of course, has to grow. So this is, you know, this is the function in Excel that we can use. So what are we gonna get? What are we gonna get for a bigger number? Well, we're gonna see it in a minute. But just to finish the exposition of this function, so we're gonna be using 2 parameters here. One is true for cumulative and one is false, and false gives you the probability of exactly k successes. So here with here we have the probabilities of various number of k or less successes. So for instance, we see that, you know, probability of 78 or less successes is 1, all right? Here we see the probability of 50 or less successes is 53%, yes? Probability of 49 or less successes is 46%, all right? And probability of 24 or less successes is 9 times 10 to the power of -8. All right, so this is a relatively small number. So this is how we can do these estimations. Now, are these, what can be said about these numbers? Well, these numbers are relatively telling us that it's very unlikely to have 76 successes or 76 failures, whatever we want, however we want to count it, in 100 trials, all right? So this is a very unlikely event, and whether we want to conclude that it was just, you know, something that happened or that the coin is biased is up to us. So what I want to do now is sharpen our intuition by running a simulation, all right? So what I am doing is I am tossing balls from this point, okay, and each ball can go left to the right with the probability of 0.5. So as a result, by ball going, you know, falling somewhere here and then falling into the bin, it generates a sequence of 0 and 1s, all right? So essentially we are generating a lot of random sequences of 0 and 1 of length 100. So that was, you know, that's what we dealt with. We were interested in the chance of getting, you know, 76 successes or 76 failures. So we are, you know, we are tossing this ball. So each pass of the ball is one sequence of 0 and 1s of length 100. So far we have tossed 10,000, almost 11,000 balls, all right? And they seem to mostly concentrate in the middle. And yes, if we do it infinitely many times, we're gonna get sort of the normal distribution here. But that is not the point that I am making. What I want you to look at is the fact that really there isn't much happening in this space, all right? We do not see any balls, you know, in this particular bin, which could be the, I don't know if this is the bin 24. I can't see it from this, but I think that was the intention. The bin count is 0, so no ball fell there, even though we are now at the number of 20, is it 20,000? Yes, it's 22,000 balls, all right? So this process is going to continue for, you know, for a little bit more. And again, notice that nothing's happening here, nothing is happening here. So this shows you how unlikely it is, say, is to have 90 successes in, you know, in 100 trials. So we're going to look at the bins in a minute. All right, we are now at 28,000, and then we're going to examine some of these bins. So we generated quite a few sequences, all right, and as it turns out, you know, almost all sequences are concentrated in the middle. They are very heavily concentrated in the middle. So this is the end of, you know, of tossing the coins or tossing the balls, and we can see here that, you know, that this bin or this bin, so, you know, bins like 76 have no, 72 have no counts, bin 77 has nothing, bin 75 has nothing, so here bin, okay, so here bin 76 has nothing, all right, and we have to move quite a bit to the right. 73 has nothing, bin 69 is the first one that has something. It has 2 balls, but notice that we have tossed almost 34,000 balls to just get 2 balls into the bin 69. So what you see here is there is a lot of stuff in the middle. So in the middle here, we have counts like 27,000, 25,000, but, you know, somewhere around 70 we are getting 0. Similarly here, you know, symmetrically, somewhere around 30 and lower, we're gonna be getting 0. So that is an important observation for our intuitions, because essentially it tells us that, you know, that if we have a sequence, okay, if we have a sequence of, you know, of 76 successes, or maybe 2 sequences, you know, with similar number of 76, 75 successes, that this cannot be generated by, you know, by the process with the median, you know, with the probability of success 0.5, that it's very likely that the probability of the success is higher, that the coin is biased, and essentially we can, you know, with a little bit of data, okay, we can assume, you know, that the bias is substantial. So that is the main idea that allows us to do estimation of parameters in expectation maximization. That is the idea that having a piece of data allows us to guess that, that there is some bias involved, that, that we can change the parameter, the main parameter, the median of this distribution from here to somewhere here. All right? So now let's look at how this is gonna play mathematically when trying to do this kind of estimations in real situations. So again, I mean, these are the charts that essentially talk to the demo that we have just seen. So the question that we posed before is, how do we read this data? And basically we read it that it's very unlikely to have fewer than 24 successes, whatever they are, heads or tails. The chances of getting 76 tails or symmetrically 76 heads are less than 1 in 10 million, all right? So a couple of pieces of data like that, and we can conclude that the coin is biased. All right, so we've seen this suggestive plot, and now, with these numbers to back us up, conclude, yes, definitely this coin was biased, and it's very, very likely that, the bias is sort of symmetric in this picture, which would be 0.6. All right, so expectation maximization, as I mentioned before, is related to clustering. All right, so here we have a plot of dots, all right, which obviously seem to form two clusters, one, around the number something like 0.8 or maybe a little bit higher, one around number 0.3 or maybe a little bit lower. We don't know exactly what the parameters of these clusters are. Moreover, we don't know which dots were generated by which, process. That is, the process that generates dots with the probability 0.8 or the process that generates dots with the probability 0.3. This guy could have been generated by this guy or by that guy. All right? But, that's the idea. The idea of soft clustering was that we don't have to know it, because for this guy we can just say, well, it's 50-50. For this guy, maybe it's going to be 55% generated by this process, and 45% generated by that process. I mean, we can actually estimate relatively reliably these numbers. So how do we go about recovering these parameters that we have here, all right, that are implicit here, that we can see with our own eyes? How do we do it computationally? And how do we do it in a way that's computationally tractable, all right? So we will investigate a way of doing it in the somewhat intractable way, and then we're gonna switch to the expectation maximization algorithm to show that it can also be done in a more tractable way. So let's do it both ways, and the reason it's for doing both ways is to see, what would be the difficulty of doing it directly from the binomial distribution. All right, so this chart summarizes what I already said. That is, we want to find the parameters of the coins that generated these dots. We have to figure out how to do it. We don't know which dot belongs to which coin, but we actually don't have to know it for sure to find the distribution parameters, and that's the beauty of the expectation maximization algorithm. All right, We will not work with very long sequences because that would be intractable on a spreadsheet. So instead, all right, I will be working with a very simple data set consisting just of four series, and the series will be short. So we have 0, 1, 1, 1, 1, all right? Then we have all ones. Here we have 0, 0, 0, 1, 0, 0, 0, 1. So these two guys are the same. So in the first we have 4 successes. In the second we have 5 successes. And here in these two, each has 1 success. So we will assume that we have 2 clusters. That is, we generate it with 2 coins. It's not a necessary assumption. Actually, expectation maximization can also derive the parameter that is the number of clusters in which this series, to which this series belong, okay? We don't have time to deal with it, but the intuition is, you know, the one that we've seen in the picture. If you had, you know, three optical clusters, the 3 parameters could be recovered by expectation maximization. There, you know, we would be just needing one more variable, that is the number of clusters, and that would be the variable that we wanted to estimate. But to simplify things, we will assume that we have 2 clusters, we have a very simple data set, and we want to find 2 parameters of the binomial distribution. So this set of parameters is denoted by capital theta, and so capital theta is theta 1, theta 2, and sometimes we're going to also use letters P and Q because that is occasionally easier to write. But in any case, we want to recover these 2 parameters. Again, seems intuitively obvious that these 2 guys should be generated by one parameter and these 2 guys by the other parameter, but we don't know that for sure, okay? It could have happened that, you know, these 3 guys were generated by one process or one coin, and this guy was generated by another coin. It's also possible that these 2 go together and these 2 go together. It's possible, it's just less likely. So we have to account for these possibilities when building our model, all right? So what is known is we have the data, so we have these 4 sequences. We assume that we are dealing with a binomial distribution, and we will assume that we have approximately equal number of points in each cluster, and we want to find out the parameters of the binomial distribution and which sequence belongs to each cluster, except that, that we will not be able to tell with certainty to which cluster a sequence belongs. So for the notation, again, we have the sequences denoted by S1, S2, S3, and S4. The clusters will be denoted by C1, C2. The parameters capital theta, and the first parameter will be theta 1. The parameter of cluster 1, theta 2 will be the parameter of cluster 2. And we will be trying to find simply what is most likely. All right, so before we do that, let's do a little bit of math, okay? So if we look at this equation, okay, can you tell me whether this equation has a solution different than 0 and 1? I mean, it's not that easy to tell, yes? I mean, it's a non-trivial equations, and actually I have the picture of 2 guys that were, you know, in during the Renaissance period, that were dueling, not with guns, but they were dueling by solving difficult equations like that, and whoever won got quite a bit of money, fame, and many other goodies. And, and there was some dirty tricks involved and all that kind of stuff, and you can read it at the link here, which is Tartaglia versus Cardano, as he's sometimes called. All right? So this equation does have a solution other than the trivial, but in general, the polynomials of a degree 5 or higher cannot be solved through radicals. That is, the way we solve the second degree equations. All right. So, I mean, that got discovered much later than that. So these guys actually dualed, solving particular cases of different equations before, the mathematics of such equations was, solving such equations was complete. All right, so here we have a different equation, yes? So here we have the equation 4 over y divided by 6, 1 minus y. Can we solve this? Yes, we can. I mean, that should be easy to solve, yes? And you can probably even guess a solution, yes? So the question is, what's the relationship between these two equations? Well, the nice thing is obviously that we have 4 here, 6 here, 6 here, but other than that, they look completely different, yes? So, and one would look simpler than the other. Well, the funny thing is that they are derived from the same task. That is, we are interested in finding the probability, okay, that maximizes this thing. We got 4 successes, 4 heads in 10 trials, okay, and we want to understand what is the most probable bias of the coin. So we are solving this, we are trying to find the P such that this thing, this binomial distribution formula achieves the maximum value, okay? So the most likely probability, okay? That's what we are trying to find. So essentially we are estimating the parameter, okay? Look, I mean, 4 successes can be generated by any coin, yes? This could be a coin, the regular coin with no bias. It could be a coin with, that in 90% gives you heads, and it still can give you 4 heads in 10 trials. It's just less likely. So what we are looking here for the most likely parameter, okay, that gives us 4 successes in 10 trials. All right. That is, that is the, the task here. All right. So remember, what our task is gonna be is estimation of parameters. We have these points, we have these clusters, and we want to find the, the means, the median values that generate these clusters. So here we have a simpler situation. We have 4 successes, and we want to find the most likely parameter that gives us 4 successes. All right? So why do we have this? All right? Well, maybe we're going to explain it in a minute. All right? So let's introduce the concept of likelihood and the log likelihood. So the likelihood is essentially viewing the probability as a function of a parameter theta. So in the previous formula, okay, we were interested in maximizing this P. So if we wrote theta here instead of a P, and we look at this expression as a function of theta or as a function of p, that would be called the likelihood. So it behaves similarly like probability, but it's not exactly the same for various reasons, all right? And what we care about is this expression, the log likelihood. Very often this is the expression we're gonna care about. So that was introduced by Charles Sanders Peirce, an American philosopher and mathematician. So this doesn't have to be exactly probability function, but you know, when we think of it, we can think of it as a probability that depends on a parameter. All right, now we had defined the likelihood and log likelihood. So the next concept is the max likelihood, the maximum likelihood. So given that we have these 4 successes in 10 trials, what is the most likely P? Okay, so that's what we were looking for, the P that maximizes the value. What is the most probable bias of the coin? And that concept was invented by Ronald Fisher. All right, so going back to our problem, yes? This is the formula, okay? And we want to maximize the value of this formula. So constants don't matter. So we have this guy here, P4, 1 minus P to the 6, yes? How do we find the maximum of a function? Well, we differentiate, yes? So if we treat P as an X and differentiate, we're gonna get this expression, yes? We're gonna get the product of the differential of the first one multiplied by the second and the differential of the second one multiplied by the first multiplied by the differential of the expression inside. So this is just differentiation, all right? So the more complicated equation comes from trying to solve this problem of finding the most likely probability or assignment, the most likely parameter, or when we have 4 heads in 10 trials, all right? Now, instead of finding this directly from this formula, we can first take the logarithm of the expression, okay? And this would give us, okay, if we take the logarithm of the expression and then differentiate, we're gonna get the second formula, which is much simpler, okay? So I don't know if I put the calculation here. Yes, here's the calculation. So we take the logarithm. The logarithm gives us 4 log p, 6 log 1 minus p. We take the derivative, which is 1 minus x, for the derivative of logarithm of x. And we make it equal 0. We obtain 4 over p, 6, 1 minus p. As the equation, we can solve it and get the final result. Why can we do it? Why can we replace the function with the logarithm? Okay, the logarithm function is monotonic. So if x is smaller than y, then logarithm of x is smaller than logarithm of y. Therefore, the maximum of the logarithm of the function is the same as the maximum of the function. So the point that gives us the maximum, the x0 for if x0 gives us the maximum of f, then x0 is also gonna give us the maximum of the logarithm of f, all right? And we deal only with positive arguments, so the logarithm here is always defined. All right, so here are examples of, of likelihoods and log likelihoods. So log likelihoods can be, likelihoods can be relatively, they are numbers between 0 and 1, but log likelihoods can be, are usually negative numbers, so they are sort of bigger in magnitude, and sometimes it is easier to see. But the main reason for using log likelihood is to simplify the computation. All right, so here is an example. Okay, so here we have a likelihood function plotted, as a collection of lines. It should, it should be smooth, obviously. And then the log likelihood looks like this, but the maximum of this guy, all right, given here 0.4, is the same as the maximum of this guy, which is 0.4. Okay, we can see it here, all right? So the function and its log have the same maximum points. All right, so summarizing this little piece of math is that it's usually easier to work with log likelihood than with the likelihood itself. All right, so it's a nice trick to know when you are working with mathematical functions. And the answer obtained by the solution to either of equation is that this probability is maximized at 0.4. All right, so now let's go back to expectation maximization. So we are given a collection of 0-1 sequences generated by two binomial distributions with unknown probabilities P or PQ, or otherwise we could say θ1, θ2. We want to find these probabilities using expectation maximization. We assume for simplicity that the two clusters have approximately the same number of points. Again, this is not this is not a necessary assumption. Some of this could be recovered from data, but it's going to make our exposition a little bit simpler. All right, so what does it mean? It means that the probability of a sequence being generated by cluster 1 is probability of a sequence being generated with parameter θ1 plus the probability of a sequence being generated by the probability θ2. These are independent events, but we have to modify it, yes, because we know that it's a 50-50 chance of being generated by either cluster, all right? So that's why we have 0.5 here and 0.5 here, all right? And we are looking for these parameters θ1, θ2. So this is the statement of the. All right, so let's look at this equation a little bit more in detail. I mean, if we have a data point such as this one, so 4 successes in 5 trials, it means that this data point can be generated by either of these, yes. However, the probabilities will be different. All right, so for instance, if we have the estimate of θ1 being 0.2 and θ2 being 0.8, we can see that the chances of getting 4 successes with this parameter is very small, okay, so it's 0.6 of 1%, and of getting 4 successes with the parameter 0.8 is 40%, 41%, all right? We get it, we get these numbers again by using this formula of having exactly 4 successes in 5 trials with the binomial parameter being 0.8. So this is, this is numerical. This comes from the table, from the spreadsheet. All right. So we see that there is a big difference that, you know, that despite the fact that either of these clusters could generate this sequence, I mean, it is order of magnitude or 2 orders of magnitude more likely that this second cluster generated this particular sequence. So we will be working with these simple sequences. We could guess the parameters, all right, but you know, even if we guess them, how do we know they are true? How do we know that, you know, that these guesses are the best guesses that we can make? So let's analyze this situation a little bit more. So if we have, say, 2 sequences, this one and this one, yes, we can look at the probability of success for the first cluster, and we can denote this probability here by P, and in the second cluster by Q. And what do we get? That probability of generating a sequence S1 is given by this formula. Yes, we have, this is the binomial formula. We have you know, 4 successes in 5 trials, so it's 5 over 4, and here we have P to 4 times 1 minus P. The probability of a sequence which has all successes is P to the power of 5. The probability of a sequence like S3 or S4 is again symmetrically given by this formula, where we have the second parameter Q, or we also gonna be using theta 2 for it. All right. So this is sort of a general description that we just get from the binomial formula. So these events are independent. So maximizing the probability could be equivalent to maximizing the product of these probabilities. So this would be the expression that we get, and if we simplify it, we're gonna get something like this. All right, we ignore, you know, some of the coefficients here. All right, so we have a complicated equation with 2 parameters, and if we try to do something about it, let's see what we get. So we are left with a product that looks like this. The product would be maximal when the first 2 functions are maximal, all right? So if we can maximize these 2 guys separately, we could very likely maximize this product, all right? And this would mean that, I mean, maximizing these guys would be like something that we have done before, all right? We take the log likelihood, we compute the derivatives, and we get some answers. So we're gonna get the answer 0.9 and Q 0.2. However, all right, this is not the right way to solve the problem, all right? So, because although the events are independent and we can maximize the product of probabilities, we didn't account for something else, all right? We need to account for the slight possibility that the sequences belong to the less likely clusters. So we can't just say that, you know, that 1, 1, 1 can only be generated by the parameter 0.9. It could also be generated by the parameter 0.2, and we haven't accounted for that. So the situation is more complicated than we assumed, and we have to correct it. Okay, so now we're gonna correct it, and we're gonna have the revised likelihood of these sequences, and now, okay, the probability of 0, 1, 1 is 50% being generated by the first cluster, 50% being generated by the second cluster. If the parameter of the first cluster is P, the parameter of the second cluster is Q, we are getting this kind of an expression. So instead of having only this part, 5 over 4 P4 times 1 minus P, we also have this part. So we got a much more complicated expression. And similarly for other sequences, we're going to have somewhat more complicated expressions. So now with this revision, all right, this is our polynomial, all right, that we would have to maximize. All right, so we have P's and Q's together, and we have no easy way of separating them, all right? And we're going to see it in a numerical simulation in a moment. So we have a complicated polynomial of degree 20, and we have little hope to find maximums or derivatives easily, even for, I mean, even if we have log likelihood, all right? Because there is no easy way of separating the variables if we take the logarithm of LPQ, of the likelihood function. All right, so let's see what, how complicated this thing is, all right? So just to give you some intuitions, this is the plot of the likelihood function, all right, using Wolfram alpha between, from 0 to 1. So we can see that, that there are two maxima here. So there are two parameters, two sets of parameters that maximize this particular polynomial. So there is more than one answer to the maximization question, all right? So the situation is, I would say, somewhat complicated, all right? And this computation of the maximums is not that easy, okay? So this is the same plot, but shown from the top. So we're gonna have one collection of parameters here, all right? So this would be P, this would be Q, and this would be P, and this would be Q. So there are two solutions to this particular collection of equations. All right, so we look at that, and we can also plot the log likelihood. Okay, so again, I mean, this is the plot of the log likelihood, and there are maxima at some points here. We're gonna see it in one of the next diagram. Okay, so here is the same plot, which also shows the maximum. So we have two solutions. Okay, so one is 0.2, 0.7, and the other assignment is 0.9, 0.2. I mean, this would probably be a better assignment. Nevertheless, there are two local maxima here. So where are we? So what is the situation? We have a very complete, we have a simple problem. Yes, just binomial sequences. We have a complicated polynomial. We have a complicated likelihood. And when we draw a picture, we have two hills, all right? So what we're gonna do is we're gonna do some hill climbing. The problem is that machines do not have vision, all right? So it is, you can think of this problem as trying to climb a hill blind, all right? So you want to get to the top of a hill, either this one or this one, all right? Moreover, you have to tell your friend how you did it, okay? So you have to have the algorithm for it, but you have to do it without a GPS, so without any positioning system, without vision. So you cannot look which way is up. You can just climb. So what you have is no GPS but you can have a compass showing north-south and east-west directions only, and you can feel whether you go up and down. So that's the intuition here. That's how we're gonna do the hill climbing. All right? So how do we do it? Well, we start going in the either south or north direction, feeling where the hill is going up. When we reach a plateau, which is sort of the max, we switch to the next direction and do the same thing. That is, we go in the east-west direction, east or west, where the hill is going up. When we reach plateau, we switch again. So in a picture, this looks like this. All right? So we go in this direction first. When we reach a maximum, we switch to the other direction, switch again to the previous direction. When we reach the maximum here, we switch to the next one, and eventually this is going to culminate in a local maximum. So the bottom line here is that this kind of blind hike might work. So how does it work with computing parameters and soft clustering? All right, so in expectation or estimation step, we compute the likelihood that the data is generated by respectively cluster 1 and cluster 2, all right? So it's going to be an iterative process. We start with some collection of parameters, and starting with this collection of parameters, we want to estimate how likely it is that our data belongs to cluster 1 versus cluster 2. And as we have seen from the previous examples, these probabilities will be very different. So we essentially have to find 8 data points. The probability that the sequence 1 was generated by cluster C1, and the probability that this sequence was generated by cluster C2. Similarly, for the second sequence, the probability of it being generated by C1 versus C2, and the same for C3, sequence S3 and S4. All right, so let's look at some numbers here. So for instance, if we take S3 and we want to find the probability of it being generated by C1, well, let's start with some parameters like 0.4, 0.9. We can estimate the probability just by multiplying the numbers, all right? So getting 0.1 with a coin with 0.4 bias is, the bias to the power, 1 minus bias to the power of 4 times the bias, and there are 5 ways of doing it, so we get about 25%. The same sequence being generated by the coin with 0.9 bias is the probability is very low, is less than 0.1%. So we know now that it's more likely that it's generated by this particular bias, but we still assume that there is a 50-50 chance of being generated by either cluster. All right. So the next step is to make a bet, all right? So we have this data, and we are asking a question. Given this data, what are the chances that this sequence was generated by the coin with bias 0.4? So we already know that, we have this sequence in our cluster. It's just the question is, what are the odds of 0.4 versus 0.9? So you imagine that you take bets, how would you, what should the odds be? How do you pay the winning, and what probability should you assign to the event? All right, so obviously what we want to know is the probability of, we have the 0.5 a priori. We have the probability that this sequence is generated by coin 1, and then we have the sum of probabilities that it's either generated by coin 1 or generated by coin 2. This is the right ratio, yes? This measures the chances that the relative chances of the S3 being generated by coin 1. And similarly, we would have a similar formula for being generated by coin 2. So here what you see is that the formula is the same, and the sum of the probabilities is 1, yes, because we're going to have the same similar expression here. So theta 1 would be here for C1. If you add, you get the identical expressions, and so the sum of the probabilities is 1 because, well, we already know that we have this sequence. So there is no mystery. We are just trying to find the relative chances of it being generated by C1 versus C2. All right, so once we substitute these numbers, we get that the probability of S3 being generated by by cluster C1 is 99%. And that comes from the fact that here we have 25% probability. This guy was 3 orders of magnitude smaller, so it really doesn't contribute much. So this ratio is very close to 100%. So we are almost certain, but not 100% certain. Similarly, we can estimate the other values. So the probability of a sequence S1 being generated by the coin with bias 0.4 or belongs to cluster C1 is 19%, 2% for sequence S2, and we're just going to round these to 100% to make our computations faster. All right, so some comments. Really, these 0.5s don't matter here. We could have, if the coins or sequences were distributed 40-60 or T1 minus T or mu1, mu2, where the sum is 1, it would still be the same formula. So here we have the general formula for the estimation of these probabilities. We would still compute the relative chances. All right? So this is the general formula for the expectation step or estimation step for the binomial distributions with two clusters. All right? So 0.5 didn't matter. We can have a general formula. But let's switch to the M step. So here's the part that we will not have time to get into. But essentially, maximizing the log likelihood, all right, so now we want to find the parameter. Now we have the data. We have some biases, probabilities that the data is generated by one or the other cluster, but we had the previous set of parameters. We want to compute the new set of parameters. So what we do, we maximize this expression, okay? So the probability, the bias theta 1 is estimated by these weights that we computed before, that ranged from 2%, 19%, and 100%. And this logarithm of these expressions. We are finding theta which maximizes this expression. Why this is a good expression? This would require some math, okay? And the hint, we don't have time to go into it. Here's the hint for those of you who would like to do it. you essentially start with the likelihood. All right, so this is the expression for the likelihood. You take the log of it and you apply so-called Jensen's inequality using the property that for each QS, QSC1 plus QSC2 is 1. I mean, you need something like that for the Jensen's equality to go through. And then you eliminate some of the unnecessary factors. So anyway, so this is where we are, and we just now gonna do the substitution and obtain the next set of parameters. So we started with 0.4, 0.9. Now we have these parameters, 19%, 2%, that was 99.8%, so we just put 1 here. We have these expressions here. So what do we need to do? We have to put something, some concrete numbers instead of a p. All right, so this would be the probabilities. All right, so if we have a parameter, this is the expression for probability. So we're going to use q instead of theta 1. So again, these are our probabilities. So we substitute it in the previous formula. We take the logarithm, we get this expression. Similarly for the next one, for the sequence S3 and S4, which is they're going to be identical. We add all of them and we will find the maximum, yes? So here is what we have, all right? So this is the stuff that we need to add in the big sum. So the sum is equal to that kind of expression. And now we have to maximize this sum. So we have to find the parameter which maximizes it. So what do we have? We have logarithm q times a bunch of numbers, logarithm 1 minus q, a bunch of numbers, a constant which doesn't matter. The general formula which we can derive by differentiation gives us q being a divided by a plus b. So after substitution, all right, this gives us 286, so this is our a. This expression gives us 819, so 3 over, what is it, almost 12. Well, so this gives us about 25%. So starting with the parameter 0.4, we went down to the parameter 0.25. So we have made one step in this, hill climbing algorithm towards estimation of a better parameter. All right. So as you can see here, this is where this estimation seems to be going. All right, from 0.4 to 0.25, we are still not there yet, and it's likely we're going to hit this particular parameter. All right, so we will not continue this computation, but I believe what we did gives you a couple of things. It gives you some appreciation of the mathematics involved, which is likelihood and log likelihood, the fact that using the logarithms for estimation is often easier than using the regular likelihood. It showed you that, that the iterative process can converge to a local maximum. It's a much simpler way of estimating parameters than trying to solve the equations from first principles. So what we have here is, this idea of expectation maximization. It's a collection of numerical methods for finding hidden parameters from data. That is, for different distributions, we're going to have somewhat different method, but the idea is the same. You essentially do local optimization, and very often this converges relatively fast. It converges to a local maximum. Expectation maximization works well because the data are with high probabilities distributed around their expected rules, okay, the expected values. So you remember the falling balls video, okay? So the fact that almost that you know that at the edges there are no balls in the bins allows us to estimate parameters of a distribution with, you know, with relative ease, okay, and relative confidence. The mathematical derivation might be complicated, but once you derive the formula, the computation is very easy. You just, you know, take logarithms, compute the sum, and maximize a relatively simple numerical expression. Expectation maximization computes a local maximum, all right? So it doesn't guarantee that you're gonna find the best solution, but it is cheap, so you can try it with different initial parameters, and that will very likely let you find a global optimum in a situation like this. All right, so this is the end of this lecture on expectation maximization. If you have questions, no. Otherwise, let's take a break. All right, so 20-minute break. Teraz działa? Dobrze. All right, so the last topic, which in a sense will summarize this series of lectures, is IBM Watson and NLP, or language processing after Watson. What we have learned so far, I believe, prepared us to appreciate a few new ideas that were implemented in Watson. We're going to discuss 6 of them. There is definitely more stuff there that would be worth discussing, but we're going to focus on 6 Watson innovations, and I will try to relate them to the topics that we have learned in the class. So we will discuss IBM Watson system, and we will point to the concepts we learned in this class. We will list 6 important Watson's innovations, and in a sense, I intend this lecture to be also a summary of this course. So here's again, I mean, the Watson the Watson's final screenshot. I like this quote quite a bit because it says, Watson became possibly the first non-human millionaire by besting its human competition, all right? So essentially it says that, well, we achieved sort of computers smart enough to be paid $1 million and winning against 2 humans. So the idea is that it opens some kind of a new era in which artificial intelligence will have a relatively big impact on the way business is done, and possibly compete with highly qualified humans. This point is debatable, all right? So it's, that was, I mean, the quote was was supposed to be humorous, but recent research in economics suggests that something like that might have been already happening since beginning of this century. That is, for the last 10 years, the machines are eliminating quite a bit of human labor, and some of this labor that's being eliminated actually requires relatively high education. Not everybody agrees with this assessment, but sorry, do I agree? I don't know. I mean, I read the arguments of both sides. Okay, so there are economists who do not agree, who believe that, you know, that it's just a temporary change, the way we've seen it, you know, in the past when some of the labor in agriculture got eliminated and people moved to factories, then the factories got automated and people moved to services. But there are economists such as Eric Brynjolfsson at MIT who believe that the technological acceleration that's happening right now is faster than that it was before, and that a substantial portion of, you know, human labor might be eliminated by the machines, leading to, you know, to high unemployment rates. Some of it that we are observing right now. So I don't know which view is right, but I absolutely agree that we have a real problem. Okay, we do have a problem with unemployment. I mean, in this country, in the U.S., there are many people underemployed, people with with high school education, but also some of the people with university education are definitely underemployed. Western Europe seems to be sort of a mixture. In some countries like Germany, the situation seems to be all right, at least according to the statistics. On the other hand, we all know what's going on in Spain, Greece, or Italy. So we have, there is a large pool of unemployed people there. Still, most of this unemployment has nothing to do with the technology. It has to do with the political decisions of austerity regime that was created after the banking crisis. So anyway, we don't know what artificial intelligence like the one embodied in Watson means, in terms of human employment and human economy in general. Nevertheless, I will argue later that it will change the way we are doing analytics, and I'm going to be using some of the IBM slides, publicly available slides, to make this point. All right, so let's look at Watson innovation. But before we do that, let's sort of review a little bit about what we have learned about human language processing. All right. So let's review why language is difficult. All right. So language is ambiguous, okay, and we're going to see some examples in a minute. We saw quite a few examples in the class. So we saw, these funny sentences that, depending on how you put the parentheses, how you parse them, how you interpret the words, you can have different meanings. This happens all the time in jokes, all right. But how the complexity of meaning is much bigger than it looks, that it seems, from some simple examples that we have seen in the class. The more typical situation is like the one that we observed when analyzing the sentence that time flies like an arrow, where there are dozens of interpretations of a sentence which seems to have only one meaning to a human. So we're gonna look at some of it. So NLP, natural language processing, so analyzing of text, remains an AI complete problem. So what does it mean? It means that essentially people believe that if you create a machine that understands language, such a machine will be able to pass the Turing test, but it will also be able to pass some other tests, like for instance, be capable of intelligent vision. Whether it's true or not, we don't know, but the problem is definitely unsolved. Language requires reasoning beyond the current capabilities of machines, all right? So Watson was capable of rudimentary reasoning, that it was able to formulate a hypothesis, that is, find a candidate answer and evaluate this hypothesis, but it was incapable, for instance, of long reasoning chains. It was incapable of taking different contexts into account. So the problem of contextual reasoning remains unsolved and is beyond current capabilities of computers. Also, language understanding requires understanding the difference between reality and fiction, all right? Machines do not have it. For machine, a text is a text, all right? We can simulate some of these capabilities saying, this is a relation that we found in the context of a particular book or a particular article, and then we can ask whether this relation is confirmed by some other evidence. So for example, when we were discussing relationship extraction and we were looking for the oldest person who swam the English Channel, we have seen different pieces of evidence asserting that different people were, the oldest people to swim the English Channel, all right, or people who swam the English Channel in general. So we don't know which one of that was true, but we can sort of try to, to simulate some of the human understanding by building scorers, which then can learn what is more probable, but still they have no idea, what is reality and what is a fiction. An argument can be made that language understanding requires having a body, okay? So in other words, the symbols, okay, of the language cannot be understood by a machine at all because a machine doesn't have a body. And there are different versions of it. One version says that, well, if you build a robot that can operate in the real world, they can learn, for instance, the concept of up and down, and with a good vision, they can learn colors and that kind, and assign colors to or color names to certain properties of the environment. But there is an argument also that since a lot of language is metaphorical and a lot of metaphors like cold, hot, refer to properties that of human senses, that basically you won't be able to understand this kind of metaphorical language without complete simulation of a human or just being a human, since it's unlikely that we're going to have ever a complete simulation of a human. So these are the two different points here, having a body, so operating in the real world, and here, the understanding might only be possible with a human body, within human body and a human brain. So these assertions are somewhat controversial. Nevertheless, NLP remains an unsolved problems, and people make different arguments why this is so. So let's look at some problems in understanding language and why we might need understanding of human reality to understand the meaning of simple expressions. So, for instance, the expression toy dog, yes, can refer to a small dog or a toy shaped like a dog, and it depends, again, the meaning depends on depends on the context. On the other hand, the same words arranged differently, dog toy, is something completely different. It's a toy played by a dog, so it doesn't have the shape of a dog, unlike this, the expression describing the, toy dog, all right? Now, similar combination, kitchen clock, is a clock in the kitchen. So it's not a clock shaped like a kitchen, it's not a clock played by a kitchen, yes, but it's a clock in a kitchen. So how do we know that, that a combination of two words suddenly has to do something with a location, all right? There is no obvious way of programming this kind of a fact in a computer, all right? Here, pocket computer is a computer that fits in the pocket, okay? So again, we have a location situation here, like here, but here, size, the relative size of the pocket computer to a pocket, well, so a pocket computer could be my cell phone, yes, I can put it in my pocket, it's similar size, but a kitchen clock, okay, if it was sort of the size of the kitchen, would be ridiculous because you need some space in the kitchen for cooking. But again, how would machine know what is the right size of the kitchen clock? And occasionally, knowing this, these properties is important in understanding a text. Water bird is not a bird that lives in water, but usually it's a bird that lives near the water, all right? So again, the location here is, we have a location here, but the location is not the, something being inside something else, but something being in the neighborhood of something else. Nevertheless, the expression is identical, yes? Now we could have some other combinations, yes? So we have kitchen clock, which is the clock in the kitchen, but water clock is not a clock in the water, it's not a clock near the water, it's a clock that's powered by water, yes? There were such devices where you had sort of a jar somewhere on the top, the water was sipping through and it was moving the clock, so that's what water clock would be. So again, we have this combination, but a priori, without a lot of human knowledge, we would not be able to guess what makes sense. Obviously, water clock as an expression appears in Wikipedia, so in this case, the machine could read a Wikipedia article and understand on some level the relationship between water and clock, that there is that the clock is powered by water. So the facts are there. Nevertheless, without an explicit statement of this fact, the machine would be at a loss. It wouldn't be able to understand the expression. And since not all combinations of nouns that are sensible to a human, all right, appear in dictionaries or encyclopedias, we have a real problem, yes? How do we understand, simple combinations of two nouns if not all of these combinations are described explicitly somewhere with respect to their meaning, all right? And this is just, dealing with combinations of two nouns. All right, so here we have a marble cake, which is a cake that looks like a marble. It's not made of marble. And again, you have to know that a cake is something for eating and that marble, it wouldn't be something that you eat. So maybe that would be enough to guess that it's about looking like a marble, but requires some reasoning capabilities, and machines do not possess it right now. Rock candy, on the other hand, is not necessarily a piece of candy that looks like a rock, but here the property is hardness. So it's a very hard piece of candy. That's what we call a rock candy. On the other hand, eye candy is not a piece of candy at all. It refers to a person. So for instance, when there is a new model of a car, it comes out of production and the car manufacturer wants to sell the image, they usually put a beautiful woman on the car, and people refer to that as eye candy. So we see that these combinations are not, are not easily guessed. Now, obviously, you can have more combinations. So what about expensive marble cake? Is it cake that looks like an expensive marble, or is it a cake that looks like marble and is just expensive? For humans, I mean, we can easily guess the right meaning, but machine would have trouble understanding, what is, and whether expensive modifies the cake or whether expensive modifies marble. So let's look at longer sentences. So if you have a sentence, Paul tried to call George on the phone, but he wasn't successful, then he refers to what? It refers to Paul, yes? But the same sentence, Paul tried to call George on the phone, but he wasn't available. Obviously, George is the referent of he. So in this case, again, the understanding of, of telephony is required to do a simple anaphora resolution. So we can't, so our features, okay, so, we did a simple anaphora resolution by creating a collection of, of features that then can be linearly combined, and depending whether the combination is positive and negative or what the value is, it would provide you for one referent on the other. But there are no obvious features, okay, here. All right, the only feature that we have is successful or available. So unless we have annotated a similar sentence before, so we have, we have dealt with this problem before, there is no way of assigning a proper referent based on a collection of features. So coreference resolution would likely fail here, all right? So these are the problems. I mean, so these are very simple examples showing that, language understanding is really quite difficult. So let's look at the ambiguity of simple expressions such as after Watson, all right? So when I put a title after Watson on my slides, all right, obviously because of my association with the project, you may think that this is about, the Watson computer. But there is, even within sort of my personal context, it can also mean, Watson Research Lab, where I worked for many years, and I retired on January 1. So for me also there is this association of with the Watson Lab, and that's basically what in the context of the talk the two meanings are, and really, I mean, however we look at it, I mean, both of them are sensible, but of course the preferred one would be this one, since I'm talking about natural language processing and the contribution of the Watson system to natural language processing. So say in the personal context there are two meanings, of which one can be, you know, that makes more sense. On the other hand, for the machine, okay, Watson can refer to anything. If you go to Wikipedia, you will have hundreds of names of people named Watson, and any of these could be, you know, could be the referent of this particular Watson. It could be the actress, it could be, you know, some shipbuilder guy, it could be, you know, one of the old chairmen of the IBM Corporation. All right? So, simple expression, many, many meanings. All right, so this is why this is a problem, because before we said that, say, maybe we can disambiguate or find the meanings of some of these expressions like water clock by going to a dictionary or an encyclopedia, yes? And that would make a computer smarter, but on the other hand, going to an encyclopedia also makes the machine more confused, because we're going to have, you know, 500 or more different references to the word Watson. So, so where's the balance? How do we go about it? All right? Well, at least the word after should be clear, but it isn't. All right? So there are many meanings of after. So again, I mean, this is taken from a dictionary. So after has this temporal succession meaning. So we had a few beers after the game. So, you know, something that happened later in time. But, you know, after him, in the expression, he will leave a trail of destruction after him. Here, it's not just temporal. This is really, you know, spatial. Okay, so this is as, you know, something, you know, going through, I don't know, the woods and destroying some you know, protected flowers, for instance. Yes. He's after a job, so he's looking for a job, so he's seeking a job. So this is another meaning of the word after. We named him after his grandfather. All right, so that's, you know, referencing or following or however you want to interpret it, but the meaning is obviously different. Next in the importance, so the princess is next in line to throne after the prince. All right? As a result of, after your bad behavior, you will be punished. All right? So maybe there is a temporal aspect here, but really what we want to convey is that it's not just that, you know, that it happened after the bad behavior, it's the result of bad behavior. It's the bad behavior that brings the punishment. So there is the result aspect of it. Here it's you know, a different variation on the theme, namely in spite of. So after all that has happened, he's still my friend. So he did something bad. It's later now, so there is a temporal aspect. But really what we want to say is there is some contrast here, that even though something bad happened, he's still my friend. And then there are, you know, some specific meanings like the modification, like the after gun is above the forward gun. So this is, you know, this is specific technical meanings. So what do we have? Well, if we take, you know, sort of the simple product of a few thousand, you know, meanings of Watson and a dozen or so meanings of after, we have a very big search space to understand, you know, to understand a simple two-word expression. So what are the problems? Well, we have a problem of representing all these meaning possibilities in data structures. We have a problem of computing with these, you know, with these meanings if you want to represent all of them. And then deciding, what is the structure of the sentence. So for instance, expensive marble cake, what is the structure of this expression? And, depending on how we structure it, we might be able to derive sort of new properties. We have a problem of encoding the background knowledge. So if we take the encyclopedia and we encode all this meaning of the word Watson, in addition to the meaning of water clock, yes, what should be the encoding? Should it be text? Should it be some kind of XML? Should it be parse trees? Should it be some kind of logical expressions? There are no good answers, and people tried or postulated, different ways of encoding background knowledge. Once we have our data structures, what is the algorithm for choosing one correct interpretation, or say two correct interpretations out of many, many millions possible? And how do we know that we are right? And finally, if we are building a system, how do we know that the system improves, and what can be done to improve the system? So obviously this has to do something with, have to do something with machine learning. Nevertheless, it is not clear how to go about it. So what Watson should be famous about is not about what it did, okay, which is played the Jeopardy game. I mean, that's fine, but there is another aspect, namely that Watson should be famous for playing the Jeopardy game so successfully without solving the natural language understanding problem. All right, because this is really the amazing feat. Yes, that Watson was able to answer questions, difficult questions, without complete understanding of the answers and without complete understanding of the questions. All right, so this is the box. The box, of course, is a very powerful computer. It's a supercomputer. It's a big machine because the answers were required in a very short time, less than 2 seconds on average. Okay, so a lot of this computation had to be done in parallel. So it had almost 3,000 processors. All right. It had a lot of memory, and that was needed because a lot of data had to be duplicated, and also a lot of data had to be pre-processed. So for instance, all encyclopedias were parsed in advance, so the structure of sentences was derived and stored. And as a result, the storage, usually when you create a parse representation of a sentence with all the annotations on the elements, you get between an order to 2 orders of magnitude expansion in size. So therefore, a lot of memory was needed, and it was sort of a random access memory because it was more easily accessible than accessing memory on the disk. It was fast because without that it would be impossible to do all these evaluations. And let's see, what else do we say here? Okay, it was doing searching. Okay, so we did talk about search here, and we're gonna talk about it again. It was searching a lot of unstructured information. Well, it ran Linux, but that is sort of less relevant to our topic of natural language processing. So anyway, the real innovation is what happened in the box. So let's look at, at what was required. So here are some of the Jeopardy questions. So for example, the question for $2,000 is, of the 4 countries in the world that the US does not have diplomatic relations with, the one that's farthest north. So obviously this kind of description would not appear in any text or any encyclopedia. So it was necessary to synthesize the answer to this question. The question for 600 in cell division, mitosis splits the nucleus and cytokinesis splits this liquid cushioning the nucleus. All right, this requires relatively deep technical knowledge, but at least we can hope that some pieces of this knowledge could be found in various encyclopedias. Question for $1,000. The first person mentioned by name in the man in the iron mask is this hero of the previous book by the same author. So here we have, a lot of coreference resolution that is required. And again, I mean, this could be our starting point, but so we can get from the man in the iron mask to the author to the previous book and then finding the hero of the book. So at least we can have some hope that by using some chains of reasoning that we can answer this question. So question for 200, if you are standing, it's the direction you should look to check out the wainscoting. So this requires the knowledge of the vocabulary and also the knowledge of how a human body sort of where to look when you look at at the wall, because this is essentially some covering at the some wall coverings. All right. So what do we have here? Well, we have a broad open domain. So there is really very little relationship between these four questions. We have complex language, as exemplified here or here. Okay, so this is not an expression of two words. This is a lot of references. In addition, for instance, in this question for 2000, I mean, the information has to be synthesized, but you also have to have some sense of directions. Okay, where's north? All right. The machines usually don't have compasses. All right, so we have these complex language, broad open domain, and now what do we have? Well, we have some prices on it. So we have to answer with high precision, because if you don't answer correctly, you lose the money, all right? And to answer with high precision, you have to be confident. So you have to have some idea, or the machine has to have some idea about how likely that the answer it's coming with is correct. And high speed, all right? So if the things can be parallelized, a supercomputer will do the job, but it's not obvious that that all of this can be done in parallel when answering one question. All right. So if we have a question like where someone was born, it could be a hard question, it could be an easy question. If you have a database which says that Einstein was born in Ulm, well, the lookup is easy. You take this as a key and you retrieve the record and you get the birthplace. All right? If you have a system doing information extraction like the one we learned about yesterday, well, we can have a collection of features, and we have the word born here, so we can have a feature that if you have the name and the word born, and then you have something that looks like a location afterwards, then this is rightly the relation of person being born in a location, yes? So here we would have a beginning of the location, and depending on our features, it could be either the end of the location here, or the location could go all the way up to here, yes, depending on what features we would have in our domain, in our named entity extraction algorithm. All right, so So prior to Watson, the answering questions that were not explicitly given in database relied on information extraction. So essentially, you would build a statistical systems like we discussed before, and this system would, assign a probability that, that Ulm is the right answer to the question where Einstein was born. Watson works a little bit differently, that surely this would be, a good thing to have, but even a sentence like this, which reads, "One day from among his city views of Ulm, Otto chose a watercolor to send to Albert Einstein as a remembrance of Einstein's birthplace." So if we can connect, birthplace to born, Einstein to Einstein, yes, and then what do we have? Well, we have Ulm here. If we can check that Ulm is a location, it could be a supporting evidence. It's not the final evidence, but it gives, it gives some additional points to the string Ulm. So this is how Watson approaches this problem. All right. So to answer Jeopardy question, Watson does not try to understand everything, but rather it operates under the principle generate and evaluate. So instead of finding the right answer immediately, it operates that let's generate many possible candidates and then let's reason somehow, the reasoning is shallow, but let's reason about each of these candidates separately and then choose the right candidate at the end. So instead of, so since we have seen from these examples that we can't find answers to Jeopardy questions in a database, sentences that we are dealing with are not necessarily amenable to information extraction. So for example, if we look at the sentence here, there will be, it's very unlikely to find, a sentence that would say Korea is the country, one of the 4 countries that, that the US doesn't have diplomatic relations with, and this one is the farther north. I'm talking about North Korea here, yes? So it's very unlikely that we're gonna have this kind of sentence anywhere and that we would be able to apply information extraction. So that's not gonna happen. On the other hand, generating, the list of all countries, yes, is relatively easy. It's a final list. Generating the list of countries with which where sort of lack of diplomatic relations is mentioned is also relatively easy, and it's a finite list that can be easily checked. So assuming that, that we can find enough evidence, we can solve these kind of problems by essentially generating a lot of candidate answers, and as long as the candidate answers are of the right type, and we can check that they are of the right type, we might be able to, to make the best guess. So the mode of operation is generate and evaluate, all right? So let's look at it in detail. All right, so here we have a sentence, okay, a question. So each year, the EU selects capitals of culture. One of the 2010 cities was this Turkish meeting place of cultures, all right? So we are looking for a city here. So how does this process of generation and evaluation happens? How do we get to Istanbul? All right, with 84% accuracy, all right, or 84% confidence. All right, so the process is, start with the question, do some analysis. We discussed some of it. So essentially, We are looking for the relations. We are looking for the keywords. We remove the stop words. We do search, which generates a lot of hypotheses. We embed candidate answers into the query terms and generate and do another search, this time using Lucene to get additional evidence. And finally, dozens of scorers weigh and combine, weigh the evidence, and then the final combination is done using a logistic regression, which we learned about yesterday. All right, so here we have our question. All right, if we continue this process. All right, we have some analysis of the question. So this is a parse tree that we learned about 2 days ago, yes? So B, okay, was and B are related, obviously. This is the lemma. So we have one place. So one of the cities, all right, in 2010 modifies the cities. Place is this Turkish meeting of cultures, all right? So that's some structure assigned to the sentence that we care about. So after that, we can generate some hypotheses, all right? So there is a bunch of places here, all right? As it happens, all of these are cities, although Turkey, of course, is ambiguous. I mean, this could also be a bird. So this is, you know, these are our candidate answers, which we then we find the evidence, and we, you know, the top candidates become Essen, Istanbul, and Sarajevo. And if we weigh the evidence, so we can create these evidence profiles for every answer, then logistic regression applied to these parameters will give us the final answer. Okay, so what we have here is that using the weights of that we learned by training the system, we get 84% probability for Istanbul and much smaller probabilities for Essen and Sarajevo, namely 11% and 7%. All right, so this is the process. This is the process of generating and testing. So here is the evidence profile. So some of the 450 features that we use is, do we have, from which documents? Is it Wikipedia, or is it, a quote from some article that we got on the web? Can we find some logical relations? That is, can we find some predicate argument structure that provides support for Istanbul versus Essen versus Sarajevo, yes? So as you can see, these evidence profiles differ. So Istanbul has high popularity, but low logical justification and low document support, all right? But it has sort of medium source reliability, almost no match in terms of time, 2010, but has a relatively high match in terms of type. So altogether, these pieces of evidence are combined. So popularity, despite being so high here, is probably weighed relatively low by the logistic regression algorithm. So the weight on popularity might be low, and therefore, despite being so big here, it actually contributes relatively little to the final answer. All right. Okay. So summarizing this, yes, generate and evaluate. It means generate candidate answers, checking them one by one and choosing the best. In generation, the usual process is using document titles. So for instance, the Wikipedia titles as candidate answers. And then we use search to find the most relevant documents to get the evidence. And evaluation is automatically scoring each candidate answer along 400 plus dimensions. So we use machine learning to find the best combination of this score. So we are essentially finding the weights for the logistic regression, which is mentioned here in this slide. So machine learning and logistic regression. So in the architecture that you've seen, all right, we're going to be looking for candidate answers using in research. We're going to be looking for evidence using Lucene search, and we have seen in our class, you know, a little bit of both. That is, of this syntax of the queries, and we have seen some operations of the Lucene engine. All right, so as mentioned before, we have these 1,000 pieces of evidence for hundreds of candidate answers. Since we have many scorers, this generates quite a few scores that have to be aggregated and then merged together using logistic regression. So what counts as evidence? So we've seen some of this in the diagram, but essentially evidence is any piece of text and any piece of metadata that this text contains. So for instance, the name of the source is also counts as evidence. So evidence comes from search. So innovation number 2 is that instead of understanding the text of the query, instead of understanding the passages, we just get all the passages, and we are doing this by searching, so we call it supporting passage retrieval, and then the evaluation of these supporting passages. So essentially we are querying sources for anything that links the candidate answer with the question. So question terms plus the candidate answer makes a new query. We run Lucene on our data and essentially retrieve pieces of evidence. So the pieces of evidence is text, but in addition to text, we also have the parsed version of the text. Yes, that is, we know what the relations are in the text. We could have done it on the fly, but then the system would be slower. Given that we have a lot of random access memory, a lot of disk space, we can afford to pre-process all our sources. All right, so the document, the passages that we retrieve count as evidence, and we really care about the relations in these passages. All right, so let's talk about some other stuff. So far we mentioned sort of generate and search and supporting passage retrieval as 2 pieces of evidence. All right. So what happens with pieces of evidence? Well, we have scorers that generates values which are numbers based on pieces of evidence associated with a candidate answer. These scores are combined to generate a composite score for each candidate answer, and the highest score candidate wins. So we already talked about it. This combination is done by logistic regression. So the innovation number 3 here is deferred type evaluation. So we mentioned it in our class before. Since meaning representation is unsolved problems, an unsolved problem, we let many scorers focus on different aspects of meanings and just put a number, okay? Sort of how much, how much meaning there is there, how much the candidate answer is related to the query. So with a slight exaggeration, we can say we don't care about meaning. Passages have no meanings for us. They only provide candidate scores. That is, they only have some aspects of meaning in the context of the question. All right, so Watson is sidestepping the problem of natural language understanding, and instead is just saying, okay, I don't know what the real meaning is, but I learned how to create some scores, and that's what I'm going to use And since there is some insight in these scores, like, you know, that there is a relation between candidate answer and the question, I can be sure, or I can be certain that most of my guesses will be correct. So we've seen this example before. Okay, we have the question about the cereal drink. We do question analysis. We are looking for a Michigan city. We have the relation that we're going to be looking for. We do the primary search, generate a bunch of candidates. We find the evidence. We get a table of numbers, and then we post the final score. So all of that we covered in the previous class. So again, I mean, the final numbers would be combined using logistic regression. So essentially, this slide just summarizes what we talked about before. So deferred type evaluation, we don't know what the meaning is, but we can evaluate some aspects of it in the context of the question. So obviously, sidestepping the problem of language understanding does not mean that no linguistic expertise was needed, all right? So Watson essentially used all linguistic tricks known to the members of the team, which were quite a few. So we used parsing, we used named entity extraction, we used relationship extraction, we used different meaning representations, so starting from text, ending with logical representation. The idea of deferred type evaluation was to use these existing technique as a collection of measurements and not as a canonical way of representing meaning. So that's essentially the novel thing, that we're going to use a bag of tricks and we're going to learn how to, you know, what really counts, which of the techniques give us the best results. So here's an example of linguistic processing done by the system. So this is another representation of a parse tree. So it's a parse diagram, parse graph. So we have a sentence, CW Post created his warm drink postum in this Michigan city. So we have CW Post, okay. Created is the main verb here. So this is a subject of the verb. It's also the theme, which is another linguistic concept. It's an agent, so this guy did this, okay? It's not that it happened to him. We have a modification that it happened in 1894, all right? We have the relation between, you know, between the CW Post and the drink postum, and the drink postum here is related to sit in a city, and the city is Michigan City. So, and this drink is also warm and cereal, and it is a cereal. So, okay, so we have these relations here. Now, it may not be obvious at the first look, but this parse is actually wrong, okay? I mean, linguistic techniques are not perfect. So what this parse says is that the in Michigan City modifies the drink postum, okay? Not the creation. It's actually the creation that was done in the Michigan City, all right? So the arrow should go from here. All right, there shouldn't be an arrow between drink postum and in this Michigan City. So despite the fact that the parse is partly incorrect, all right, Watson can find enough evidence to connect the drink postum with the correct Michigan City. So, well, to summarize what we talked about on the sort of computational linguistic level, yes, we essentially said that by leveraging many different techniques, Watson was capable to produce the right answer. And this technology, the name of this technology that we used internally is Deep QA. All right, so we had these sentences, these questions, how do we represent all these meaning possibilities? How do we compute with words as data? How do we choose the right representation? How do we encode background knowledge? How do we find structure of the sentences? All right. So we didn't answer these directly. We just said we're gonna sidestep them. We're gonna just take whatever we can, do different tricks, and we're gonna use machine learning to see what is right. We will not try to comprehend it. So now we have two more questions to answer. How do we know we are right, and how do we improve the system? So Watson, of course, had to know whether the answer is correct, because otherwise betting wouldn't be possible. So how do we know that, that the algorithm provides the right answer? There is no a priori decision that can be made, so therefore the innovation number 4 in Watson was to use independent modules, okay, so independent scorers coupled with rigorous testing. So we were trying many different algorithms, we were trying different knowledge sources, and we were measuring the contribution of each algorithm and the source. So if the source didn't contribute any new knowledge, it didn't improve the results, we would remove it or change it or do something with it. Similarly, if the algorithm didn't have any impact on the performance of the system, it didn't go into the final version. So we had to test the contribution of the new algorithm and a source, and that was done in a very systematic way in so-called weekly runs. Since the modules were developed independently, the people who developed the scoring modules were sitting in one room so that they were able to iron out the problems, mismatch, for instance, in Java data types. So this is how we were doing error analysis. So essentially, we have run about 10,000 experiments in the course of the project. Each experiment consisted of taking the system and applying it to between 2,000 and 5,000 questions. And each experiment generated up to 0.5 terabytes of data, which was then available for analysis. So this is, this is the record of all experiments until February 28. Some of the first experiments were not recorded because we didn't have this tool, but the last 3 years before the game, all experiments were recorded, and they are still available somewhere, probably on one of the hard drives. So what did we measure in the experiments? Well, we measured the performance. That is, we were looking, for instance, how many questions were correct in the first place, because the questions were scored. So here we have the number like 1940. We were looking in difference, so we had experiments. We had experiment here. So here we have experiment 8,594, and here we have the experiment 8,608. It had to be run on the same set of questions. We're looking at stuff like, average precision. So the average precision here is 76%. Here we have 84%, which is obviously better. We were looking at, many other numerical scores. But in addition, okay, I'm sorry, I don't have a slide, so let me just go back here. But in addition, we were looking at all questions, whether they were answered correctly or not, and you could examine the evidence for each question and the scores posted by many of the different scorers. So we had a complete view of what happened in scoring a particular question. So this diagram shows the performance improvement. That was the baseline system. So the team, which I wasn't the part in 2006, was working on question answering using the information extraction approach, that is finding, you know, the sentence which might have possible answer, extracting the entities, and then matching these entities with the question. So the performance was here, okay? That was definitely not good because, I mean, I will explain the, you know, what the axes are, but just to give you sort of a general sense, this is not good performance. This is the performance of Jeopardy champions, and the red dots are performance of Ken Jennings. So as you can see, even the final system that we have here, it wasn't clear that it's going to outperform, you know, the masters. Okay, so there was actually quite a bit of uncertainty as to who's going to win the game. We are seeing successful performance improvements here. This line, okay, had to do with introducing the idea that the answers will be found in Wikipedia titles or source titles. All right, so instead of doing information extraction, we're just gonna put a lot of sources and we're gonna treat titles as the answers. And default to, so this would be a default, that is, first look for a title. If you can't find good enough answer, which is a title, then possibly attempt information extraction or another method. So let's look at this diagram. So obviously the machine can choose whether it answers a question or not. Okay, it can just say, I'm not going to answer this question because I don't have any good candidates. Yes. So the machine can answer, you know, 50% of the question, or it can choose to answer only 10% of the question. And usually, if machine chooses, you know, to answer only 10% of the questions, this is going to be correct answers because, you know, there is enough evidence to support it. But answering only 10% of the question does not win the game. To win the game, the machine has to answer about 50% of the question. All right, so somewhere here between 30% and 80%, and 50%, and the accuracy has to be somewhere here, around 90%. This is the spot. Now notice that being able to answer a question does not depend only on knowing the answer. It also depends on other players, because if the other players can find the answer faster and buzz before the machine wouldn't answer the question. So knowing the answer is not enough. So therefore, for a real performance, given that the machine will not always win the buzzer, the machine should be able to answer most of the question, and most of them have to be answered accurately. All right, so this was the challenge, essentially, to go from this line to, you know, the line that would be somewhere here. All right. What you see in these, I mean, these are successive improvements. So some of them had to do with the introduction of sources. So somewhere, you know, between this line and this line, we introduced quite a few additional sources. Most of this improvement, I would say, is due to some algorithmic changes. Sources contributed quite a bit, and we're going to have some specific numbers in a second. But, you know, the ability of the Watson system to win was dependent on the team being able to measure the progress and being able to examine to examine what we are doing right and what we are doing wrong. So let's talk about sources. So the innovation number 5, and it was related to the fact that we are looking for titles as the answers to the question, was background knowledge engineering. And here we have essentially a couple of things that constitute this background knowledge engineering, which is source selection, source preparation, source expansion, and then testing the contribution of sources. Adding more data does not have to improve the system. So adding more knowledge is not necessarily good. We saw it, with the Watson example, after Watson, that adding the encyclopedic knowledge about all possible meaning of Watson could very likely confuse the system. And similarly, for question answering, people have done research previously showing then, say, adding, 500 megabytes or a gigabyte of additional text might decrease the performance of a question answering system. So sources had to be added selectively, they had to be prepared right, and we had to do a lot of testing to make sure that the sources we are adding are actually improving performance. To give you one example, many of the questions in Jeopardy ask about famous literary work. So it could be a quote and you're supposed to give a title. It could be a quote you're supposed to give an author. Or it could be a quote and you are supposed to find the missing words in the quote. So at some point, we decided that we're going to add the Gutenberg archive, which has most of the classic works, at least all of the classic works that are out of copyright, to the system. And that way we should be able to answer the questions about, who authored the particular quote, or answer the question, which words are missing in a particular quote. So that was a relatively large database or relatively large collection of text, and it had absolutely no positive impact on performance. It had slightly negative impact on performance. So as a result, we decided not to do it, and instead we selectively added about a few hundred books. And even for these few hundred books, we didn't add everything. We added, sort of the opening paragraphs of each chapter. And that was much better, at least. I mean, it didn't have an obvious positive impact, but it didn't have the negative impact on performance. So source preparation, well, we were putting everything in the track format, so we can use the title as the answer. We process text syntactically and semantically before using it supporting passage retrieval. Okay, so that is source preparation. A comment here that that this kind of work is also essential when you do applications. So, for instance, when we built the application of Watson for help desk support at IBM, we also used, the same approach, that is the answers were something that looked like a title. Essentially, it had it had a tag, answer or answer list. So, so here I put a comment here that, that this is something, we discussed Solar and Lucene, and we discussed the track format, we looked at the Reuters data. So essentially, what we were doing in Watson was following the same idea, that is, annotate the sources well enough that when you are looking for data, you can take advantage of the tags. So you can do faceted search. These are the numbers that show the impact of source acquisition and transformation and source preparation. So, for instance, the accuracy with Wikipedia only, okay, so this was our starting point, was 59%. That was definitely insufficient. With after adding, experimenting with quite a few sources, this accuracy would go to almost 67%, and then adding some web sources further improved the accuracy to about 70%. Precision, at 70% answered, okay, we get almost to 90% correctly answered. So the impact of source engineering was really substantial. But also notice that while the Wikipedia text was relatively small, so we had about less than 4 million documents and 13 gigabytes of data, adding these additional sources increased the size of the database. I mean, it was it doubled the size. Here, using the web data, obviously web data was a lower quality, so to get a 4% improvement, we had to more than double the amount of data here. The number of documents didn't grow as much because we were adding data only to the most important topics from Wikipedia. So we discussed a few of these Watson innovations. This is obviously not all. So there is quite a bit of stuff in IBM Journal of Research and Development. You should have access to all the articles from this journal. You can either do a Google search on it, but I also left the copy of the journal, the electronic version of it, here with the school a year ago when I was giving a talk on Watson. Obviously, this story of Watson innovation is not ending with 20 articles that are published there. There is about more than 50 patent applications and several patents already granted. So if you want to know more, you go to Patent Finder at the uspto.gov, okay, and you can find quite a few Watson patents. So what is going to happen next? All right, so IBM has plans for using Watson in several places, and some of the stuff that was announced already is using it in healthcare with several healthcare facilities, call centers, financial services. All right, so there are several opportunities in healthcare. So for instance, you can use Watson capabilities to decide whether certain treatment is plausible or not, okay? Will it likely to improve the healthcare of the patient or not? Does it make sense, to give them this particular drug or not? All right, and Watson can analyze many pieces of data and essentially provide evidence for and against, and it would be up to the doctor to decide, what should be believed or not. It can obviously be used in diagnosis, okay, because, well, diagnosis is like answering a question. You have a collection of symptoms, and you're asking a question, okay, with these symptoms, what is the disease? That the answer is a disease or a collection of diseases. I mentioned call centers. One of the first prototypes that we built had to do with answering technical questions. And again, we could measure Watson performance sort of with a very simple technology. Even without supporting passage retrieval, we got about 10% improvement in quality of answers over keyword search. So, some of my colleagues are still working on this stuff, and this has a potential of being, profitable relatively fast. And the reason is, one that I mentioned before. Many people work in call centers. Many of technical calls take a long time. So if you can shorten the average length of a call even by 10%, it's a huge economic impact and you know, a huge impact on people's mood. Yes, you don't, you know, you want your problems solved fast. Financial services, there is a lot of financial data. A lot of that data is in text. So again, Watson can be used to create some scenarios. This is essentially an analytic play in automotive. So the idea is to analyze vast volumes of information like customer sentiments, sales data, historical pattern, and based on this data mining activity, you know, create some insights that then could be applied in sales. Government, well, all government agencies have a lot of data, so being able to analyze it or being able to answer questions of people dealing with government services would be of huge value. And similarly here, the retail is in a sense like automobile, where you can either analyze a lot of data or you can help customers choose the right products. This is an IBM slide from 2012. And it sort of shows the difference between playing a game and applying this technology in industrial context. Yes, using it in call centers or for medicine. So essentially going from playing the game and showing what's possible to actually using it as a profit generation activity. So in a game, you have one user. In a call center, you can have thousands of users. Yes, so the architecture would have to be somewhat different. Jeopardy is one question. When you're answering a technical question, there are, you know, usually follow some kind of path of reasoning. So many questions can be asked, and they are dependent on each other. The input to a Jeopardy question is short, 2 sentences. If you want to diagnose a technical problem, the text can be very long. In Jeopardy, you answer a question and you're done. Here, you know, you are dealing with many questions. So for instance, in medical diagnosis, you follow a certain path. New data comes in, for instance, from testing the patient. So you have to manage the context. You have to manage the state. In Jeopardy, you really care about the top answers. Here, you would like to have more than one possibility in diagnosis. There is no guarantee that the top answer is the right one, and it really doesn't matter. You want to bring some possibilities to the attention of the doctor. We are doing retraining in about 5 days. For financial services, you would need to essentially be able to ingest the content in real time. Supporting evidence was hidden in Jeopardy, but if you talk to the doctor wants to know what is the reason for this particular suggestion of a diagnosis. So the doctor wants to see the evidence and wants to see the reasoning. So some stuff that is understood only by the creator of the algorithm has to be presented now in a way that can be understood by a person who has no idea about computer science or has little idea. Text-only input for Jeopardy. Here, the input for the question could be a text, it could be a table, and also later probably some images. So here we have question and answer. In medical, we have to manage cases, and we didn't care that much about security. Yes, we had, a separated system. So the security was very easy. I mean, it wasn't connected to anything. It wasn't connected to the internet. So essentially, you lock the room and you have the security, yes? But in in a system connected to the internet. There are privacy issues, so medical stuff or financial stuff is highly sensitive, so you have to have some idea about what evidence you can present and how you're gonna secure the system. So, given all that, yes, what does it mean for next steps in computing? All right, so IBM is claiming, okay, again in this Edge 2012 talk, that we are entering a new era in computing, all right, that essentially from simple systems that were based on tables, and then systems that that were predicated on algorithms. We are entering the era of learning systems, that the systems that can adjust their performance based on the data that they acquire. So this is, so that's the IBM claim. So it seems to me from my experience that essentially we're gonna, instead of doing sort of text mining as a batch job, we're gonna see sort of the concept of a text mining factory where we'll have, as in Watson, integration of multiple modules based on machine learning. We're gonna explicitly trade off between the coverage and quality. So, how many questions we can answer versus how well we can answer questions. And we will have to deal with real-time evidence evaluation. It also means that there will be some new organizational structure that would support, building and operation of these kind of new kinds of learning systems, in particular data mining or text mining factories. So specifically about text mining and language understanding. So after Watson, language understanding remains AI complete. We have all these techniques, but we haven't solved the problems. So this Watson could be viewed as an inspiration for creative progress. Instead of trying to solve these problems, maybe sidestepping them sometimes works better. Opportunities to explore. So architectures based on huge amounts of random access memory. That would be one thing. Massive textual data sets, orders of magnitude bigger than Jeopardy games. So some people are already going into this space. Dialogue interaction, okay, Watson didn't have much of it, but if we view language as a collection of actions, maybe this is a better perspective than viewing language as a collection of relations. And we will need some new math tools, maybe tensor calculi, as some people are postulating, or some exotic algebras that haven't been tried yet. So we can stop here, and if you have any questions, I would be happy to answer. All right, so questions about Watson, questions about information extraction, questions about the test tomorrow. All right, so okay, so let's talk about the test tomorrow. So what should be on the test? All right, so what did we cover? Well, we covered stuff like language preprocessing, so you should know something about stemming, lemmatization, that kind of stuff. We covered the Bayes theorem. We covered naive Bayes. We talked about, okay, naive Bayes classification. So we talked also today about clustering. And we talked about some architectures, yes? So search architecture, Watson architecture. So let's see, did I miss something? What did I miss? So certainly you can expect a question, related to Bayes' theorem or naive Bayes, something related to clustering, something related to similarity between documents, so matrix representation of the documents. Nearest neighbor classification, yes, did we cover that? Yes, I think we did. So that would be another topic. All of these are simple. And then, some more open-ended stuff, like here we have a problem. What would be the architecture to solve this problem? You can, you can apply the techniques that you heard about in the class. So that's going to be more open-ended, but the scoring for me of it is relatively simple. That is, does it make your solution make sense, and how many of the techniques that we discussed in the class are present in the solution? I mean, not just that they are listed, but that they sort of make sense from the point of view of the quality of the results. So, yeah, so that should be it. And any more questions about it? So you know what's going to be on the test. No, odpowiedzi powinny być w miarę szczegółowe, to znaczy ja chcę widzieć, jak Państwo rozwiązali problem, co zresztą jest lepiej dla wszystkich, dlatego że jeśli, powiedzmy, odpowiedź jest niepoprawna, a metoda jest dobra, no to ja jestem gotów dać za to punkty, prawda, więc to jest lepiej dla wszystkich, jeśli całe rozwiązanie jest pokazane na egzaminie. Proszę?
Przykład zadania.
No przykład zadania, no to właśnie przykład zadania może być taki, że jak Państwo na przykład macie tą tabelę w naive Bayes, prawda, i są pewne tam dane, jedynki i zera w tej tabeli, no i tutaj jest nowy wektor i on będzie, czy to będzie 0 klasa, czy to będzie klasa 1 i dlaczego? To jest proste pytanie, prawda? Inne pytanie, no powiedzmy, no w rodzaju właśnie coś w rodzaju, znaczy może nie dokładnie o lekach, że powiedzmy ten lek jest skuteczny powiedzmy w iluś tam procentach, ale jeśli pacjent miał coś tam jeszcze, to powiedzmy lek jest skuteczny w jakiejś... Twierdzenie Bayesa, tylko po prostu zastosowane do pytania, które wygląda nieco inaczej niż to, co robiliśmy w klasie, ale to w zupełności wystarczy. A jeśli chodzi, powiedzmy, o powiedzmy K-means clustering, no to na przykład może być, tutaj są jakieś tam punkty no właśnie, no, skomasować te punkty w dwie grupy, prawda? Używając na przykład two-means clustering, zaczynając od powiedzmy pewnych punktów w jednej grupie i innych punktów w drugiej grupie. No bo ja muszę Państwu podać, w jakiej grupie trzeba zacząć, żebym po prostu oceniał to, żebym miał tylko jeden temat do ocenienia, a nie na przykład 27, prawda? Więc takie może być pytanie. Nie wiem, co jeszcze.
Ten egzamin jest na ocenę czy na zaliczenie?
A to Państwo się powinniście dowiedzieć w dziekanacie. Ja nie mam pojęcia. Co mi powiedzą, tak będę oceniał. Mnie jest wszystko jedno, czy to jest na ocenę, czy na zaliczenie, prawda? Znaczy mój system jest taki, że po prostu ja daję punkty za zadania, no i w zależności od pewnej ilości punktów to jest ocena. Czy ta ocena się nazywa czy ona się nazywa 5, no to do mnie to nie robi specjalnie różnicy, prawda? Nie ma egzaminu poprawkowego.
Jeżeli ktoś nie zaliczy, to co w tym momencie?
No to ja nie wiem, to Państwo wiecie, ja nie znam systemu tutaj, ja nie wiem, co się dzieje, jak się nie zaliczy. No to czasami w życiu tak jest, że człowiek ma tylko jedną szansę, prawda? No. Więc, no ale Państwo znacie pytania, to chyba nie powinno być tak trudne, prawda? No nie, to prawda, że tak się mówi i to prawda, że to jest wszystko w jednym tygodniu, że Państwo nie macie czasu tego przemyśleć, to jest poważny problem. No ale ponieważ ja jestem świadomy tego problemu, to również będę brał to pod uwagę. O.
No i do tego mam jeszcze egzaminy w przyszłym tygodniu.
A to już nie jest mój problem. Ale to dopiero w przyszłym tygodniu, a Państwo macie weekend i to długi.
Ale w weekend to jeżeli mamy teraz jeden dzień na ogarnięcie tego przedmiotu, w weekend mamy ogarnąć 5, to się tak nie da.
No to są problemy dla innych wykładowców. To proszę rozmawiać z innymi wykładowcami na ten temat. Ja już na nic na to nie poradzę.
Oni też nie widzą problemu.
No to takie jest życie studenta. No ja też byłem studentem kiedyś, prawda? Dobrze. To co? To zobaczymy się w piątek. Czy są jeszcze jakieś pytania? O, materiały za 10 minut. Dobrze. Zaraz to mogę odczepić.